relational algebra, I have given you a little bit all note. So therefore, make sure you refer to that as well as UCSC note. Okay. Uh, right. So what is, or why do we need relational algebra? Or what is relational algebra? So basically, relational algebra is the theory behind SQL, or rather theory behind relational databases. Right. So relational algebra is the theory behind relational databases, especially when it comes to querying data, right? Querying data and relating data. So therefore, in the background, we have learned little bit of relational algebra, but not relational algebra. What we have learned is relational theory, right? Relational theory. So that is how we came up with the concept of primary key, the concept of foreign key, right? So the foreign key must map into the primary key and so on. So we have built database based on relational theory rather than just in ad hoc manner you connect one table to the other. That is network databases. Okay, that is network databases people tried out in 1980s, 70s. So relational algebra is an extension to the relational theory, which we can use when it comes to querying data. Because once you insert data, so why do we keep data? Because later we want to retrieve data for reports, analysis, and there can be some inquiries. So in that situation, we need to get data. But the reality is we don't just take data from one table. Maybe some data from this table, another set of data from another table, maybe another set of data from another table, and combine those data together and maybe generate a report, maybe generate a summary detail. So maybe we want to do some analysis. So when we retrieve data from multiple tables, so because we create database using relational theory and also the normalization also part of the relational theory, using relational algebra, we can understand what is the best way to retrieve data. Because when you retrieve data from multiple tables, the things can get complicated. Actually, it is complicated for ordinary person. So therefore, we need a systematic approach. That is what engineering is all about. Something which is complicated for ordinary person, it is not complicated for engineer because engineer one in one hand, of course, engineer is a talented person. On the other hand, engineers knows the systematic way of doing things. And relational algebra is the systematic way of querying data from relational databases. Okay. So therefore, there's something called relational algebraic rules, notations, so that you can understand the theory. Okay. So first we are going to look at the basic notations and operations. Just like in normal algebra, in maths, so we have operations like add, subtract, multiply, divide, and we apply those on either numbers or algebraic variables like x plus y. X squared minus y squared, that is x into x minus y into y. So that is normal algebra. So then we learn Boolean algebra, right? Boolean algebra. So that is operations are AND, OR, XOR, NOT, and those are operated on Boolean variables, maybe A and B, bar. That is Boolean algebra. Again, you have the operators and variables. Here also operators and variables or constants. In relational algebra also we have operations, and we can apply those operations on variables. So those variables are basically tables and views. So therefore, this is a little bit more complex also because our variables are now tables, views, the result of another query, and so on. Just like we can write A plus B dot C. So this AND operation is on result of this operation. And that result is AND with this. So similarly, we can do the same thing with relational algebraic theory also. Right. First, we will look at what are the relational algebraic operations. So the operations are selection, projection, union, set difference, and Cartesian product. And just like in Boolean algebra and normal algebra, we have symbols. We have symbols for these operations. Like selection is sigma, projection is phi, union is this, set difference is like this, Cartesian product is like that. So same thing, okay? Same concept, same structure, but we operate on tables, views, and so on, or result of another query. Right, so let's look at the selection operation. Selection. By the way, this is very simple. I don't think that this is very difficult thing. Right, so selection means from your data, it can be table or view or results of a previous query. So your data has set of records and set of fields, and maybe student details. Student number one, nimal@gmail.com, maybe date of birth and so on. Student two, Kamal, and blah, blah, blah. So then what is mean by selection operation or select operation? Sigma. We select only some records. So maybe there are 100 records, but after the selection, we get only maybe one, or maybe 10, or maybe 5 records. So that operation is called selection. So that means we take only some records based on a logic or condition. Okay. Maybe students who have done their payments. Okay. Or if it is employees having salary greater than 200,000 rupees. So that is called selection. So selection means you select only selected rows based on a condition, which we often need, right? Which we often need. So that is called selection. Okay. So this is an example. From this table, you select only these two records. That means you can see that where the department number is 7. So this is how you write it. Sigma, where D number is 7 from employee. From employee, select based on this condition. Department number is 7. So when you select, what you get is only these two records. So that means you don't have 3 records now. The result of this operation is these 2 records. But we get all the fields, but only for these 2 records. So that is called selection. Right? So that condition can be equal, not equal, greater than, or greater than or equal, less than or equal, or any other combination, like this condition and that condition. So you can see in relational algebra, this condition is Boolean, true or false. So therefore, in the condition part, we can use and, or, and not, or even XOR. Because this part is Boolean, condition is Boolean, but this expression is relational expression called selection. Okay. So if you have any doubt, you need to ask, because this is the basis for SQL. So there are plenty of students struggle developing a system, even the final year project, because they don't know how to write a query. So they have a requirement, but when they write the query, they don't get the expected records. Sometimes more records, sometimes less records, sometimes unrelated fields. So that means they have not understood relational theory, relational algebra. So the root cause is here. So you can't go and fix SQL without first understanding what is relational algebra is. So therefore, this is where you need to be very serious, because we can't fix symptoms. We need to fix the root causes. So these are the root of writing correct SQL query. Right. So that is called selection. So the next operation in relational algebra is called projection. So we use the symbol phi. So projection means from your data sets, you project only selected fields, maybe just one field, two fields, and so on. So that is called projection. Okay. You project only some fields, not all the fields. Okay. So this is an example. Same table. So earlier we had three fields. Maybe we are only interested in employee number and employee name. We are not interested in department. So we can project. So how do you write? Project employee number and employee name from employee table. So that is how you write it. So the result is this. If your original data set is this. So we use phi for projection. It's just a notation. Remember, even the math subject is based on notations, axioms, and theorems. So this is just the definitions, and so it's like we defining what is add operation, subtract operation, AND operation, O operation. Now we define another set of operations called selection, projection. But these operations are for data sets. Data sets. Okay. And usually this order doesn't matter. We don't care whether it's name, comma, contact or contact, comma, name in general. But there are situations this order also matters. Right? It depends on the later, how do you write your SQL queries. Right. So the third,
Excuse me, sir.
yes,
In that example, the
yes.
second part, get first name and last name of all employees. The second one is wrong, right?
What is my second one? This one.
Next one.
This one.
Yeah, the left side one.
Ah, yes. Yeah. Yeah. So I'll fix that. Sorry for that. Okay. Yeah. Thank you. So it should be name, contact number, but the contact number is not there, right? So it says first name. I have just copied the first one. Yeah. So that is wrong actually. So it's assuming that there's a table called student. You want to get the name and contact number, right? Not the last name. Yes. That is a typing mistake. Okay. I'll fix that. Okay. Thank you. Yeah, it must be get first name and contact number of students. I think this part is correct, but this one is not modified. So this must be contact number. Okay, right. So let's move on to the union. So union operation is similar to the set union operation. Right, set union operation. So that means if you have two data sets, so this is my R data set, this is my set data set, S data set. So this has set of records. Say student 1, 4, 5. And here we have student 4, 6, and 5. Rest of the fields are there, right? So this has student 1, say Nimal, Nimali, and Kamal. So this one has again Nimali and two other students like Rehana and Chaman. Now, what is mean by R union S? So R union S means you take all the records which belong to either R or S. But if it belongs to both, you take it only once. So therefore, the results will have 1, 4, 5. 5 is already taken. 4 is already taken. And additionally, you will have 6 also. So that means 1, 4, 5, and 6. So that is called union. Just like set union. But you don't take the same thing twice. Right? Duplicate tuples are eliminated. Eliminated means eliminated once. Right? So don't think that the duplicated elements are not at all taken. Right? So you don't take the second duplicated element is eliminated. So that is called union operation. So you can do, now you can see so far we work with one set of data. One, so that means this is unary operation. Projection, selection, unary operator. It works on one set of data set. But now you can see union operates on two data sets. It's sort of a binary operation. So earlier we called something like sigma from X, phi from Y. Sorry, sigma from X, phi from Y. But union is X union Y. X union Y. So that means it's a binary operation. So you need two set of data. And those two set of data must be compatible. You can't union tomato with potato. But you have a set of tomato and another set of tomato, you can union. Maybe they have different tables, but maybe the records are compatible. So here you call it F name, but here you call it Fn. Here you call it L name, here you call it Ln, but it's the same thing. If you know that it's the same thing, though it's in two different tables or whatever, so still you can do the union. But if this is F name and last name, and if this is something else, so then you can't do it. At least you need a common field, which uniquely identified. Then you can do the union. Okay. Right. So the next one is set difference. So set difference is, so here you have set of data. I'll take the same example. So what is R minus S? So R has 1, 4, and 5. S has 4, 6, and 5. So from these records, we take out if that particular record is here. You can see 1 is not here. So therefore 1 will be in the final result. 4 is here. So therefore 4 is removed. 4 is not in your final result. 5 is removed because 5 is here. So therefore your final result is only 1. Only 1. That is R minus S. Then what about S minus R? S minus R may be different from R minus S. But here R union S is same as S union R. But here R minus S and S minus R are different. So 4 is here, 4 is here. Therefore, you don't take 4. Now I'm interested in S minus R. 4 is not taken. 6, yes, 6 is here but not here. So 6 is in the result. 5 is here, 5 is here. So therefore 5 is not taken. Only 6 will be there. So you can see S minus and R minus S are two different things. So in general, S minus and R minus S can be different, but always the union is the same. It doesn't matter whether left or right for union, but it matters for set difference. Okay. So this is an example. Assume that these are compatible, union compatible. That means set difference also compatible. So now what is student minus instructor? That means he or she must be a student, but not an instructor. Assume that these are sort of unique. Assume that Kapila is only Kapila. There's no two Kapila. Okay. So Kapila is here. Kapila Dias is here. So therefore, Kapila Dias won't be in student minus instructor. Nimal Pereira is here. And Nimal Pereira is here also. Therefore, that is also not taken for student minus instructor. I'm interested in this. Ajit Silva Here you don't have Ajit Silva, so therefore Ajit Silva is in our result. Rohan Mendis, no Rohan Mendis here, so Rohan Mendis is here. So then what about the instructor, which is, he or she must be an instructor but not a student. This is student but not an instructor. So then you need to do the reverse way, right? Reverse way. So Sunil De Silva, not here. So Sunil De Silva must be here. Kamal Soisa, not here. Kamal Soisa is here. Saman Silva, not here. It must be in the output. Then Kapila Das is here. Nimal Pera is here. So therefore not in the output. So that is called set difference. Okay. So these two data sets must be compatible. Compatible. Okay. Then only we can do the difference. Because this is a binary operation, just like union. Union also must be compatible, right? You can't union apple with tomato. Right, our final operation is Cartesian product. So this is pretty similar to the Cartesian product in sets. Remember when we have two sets, A, B, and C, Cartesian product, P, Q set. So the result is a set having ordered pairs. We have done that on the Boolean algebra. In maths, A, P, A, Q, B, P, B, Q, C, P, C, Q. That is your Cartesian product. That is sets. That is sets. That is X Cartesian product Y. So then what about the Cartesian product in relational algebra when these are data sets? Again, it's a pretty same concept. Right? So let's take a practical example. Do we have practical example? Yes, we have a practical example. So this is my employee table. This is my department table. So when you take Cartesian product, it can be two different things. Remember, for union and set difference, it must be compatible. Apple with apple, tomato with tomato. But here it can be apple and tomato also. But at the same time, they can be different, but they must be related. For set difference and union, they must be the same. Here, they can be different but related. Related. Otherwise, it won't make sense. If it is not related also, we can define Cartesian product, but to make sense, it must be related. But even without relationship, yes, we can write the Cartesian product. So how do you write the Cartesian product? Just like sets Cartesian product, you take first record from the first data set and combine with all the records in the second data sets. That is your first result. 179 Silva 7, 4 finance 857. So then you combine this with this record. 179 Silva 7, right? 179 Silva 7. Then 7 sales 179. So that is the second one. So these two records are combining this with this, combining this with this. So similarly, you combine this with this with this. You get another two. That is one and yes.
Then we have to take all the columns in both the tables and join together.
Yeah, all the columns. All the columns.
Okay.
And if you are not interested in some columns, then you can later on top of this, you can do the phi operation, projection, saying that I am interested only these. So that is our next step. Combining these operations together, just like in arithmetic, we can say 5 plus 2 into 3. So therefore, we can later combine. Still, we are only looking at one operation at a time. So therefore, you need to take all the columns. So then with 342 dies, you combine with 4, and also 342 dies, you combine cells. So if you have 3 and 2, you get 3 into 2, 6 records. If you have 5 here, 8 here, you get 40 records in the result, Cartesian product. Okay. And theoretically, if there's no connection between these two, still we can write the Cartesian product, but it won't make much sense. So ideally, there must be some connection to make it practical. Right? For example, here you can see department number is common. So then only it make practical. Otherwise, mostly it is not practical to write a Cartesian product. Of course, you can write the Cartesian product, but it may not be practical. But it's more practical when there's a connecting field, which must be a foreign key also, to make it really, really, really practical results. Okay. So this is the basis for joins in database queries, right? Later we'll look at inner join, outer join, and so on. So this is the starting point of join, Cartesian product. In SQL, we can write Cartesian product, right? Because SQL support all these operations. So if I have two tables, I can write a Cartesian product. But I try to stay away from SQL right now, right? Because I like you to learn the theory without, maybe you already know a bit of SQL, that is fine. But let's not talk about SQL until we finish our discussion on theory. And then only we'll go to the SQL. So therefore, if you don't know SQL, actually that is even better for you because you just purely learn the theory here. Right, so the next one is intersection. And you know what is intersection is, right? Intersection means you have again compatible data sets. But if the particular record is in both data sets only, you take it, otherwise you don't take it. That is as simple as that. Okay. It's something like a person who is both student and instructor. That means he is a student as well as he is playing the role of an instructor. So here we have Kapila Dias playing both roles and Nimal Pereira playing both roles. No one else. So therefore, this is our intersection. We use the same symbol as set intersection. Right. So let's look at some features. Just like you know that 5 plus 2 is same as 2 plus 5, which you know, right? But someone must have told you, right? And at the same time, you know that 5 minus 2 is not same as 2 minus 5. Though 5 plus 2 is same as 2 plus 5. So therefore, you need to pay attention when you learn a new concept. What are the things we can do? What are the things we can't do? After sometimes it will be a sort of a normal thing for you. That is fine. So normalization, familiarization. But first of all, you need to seriously think about it. What can I do? What I cannot do? Right. So the first rule is, remember we learned some rules for Boolean algebra also, right? A dot B same as B dot A plus B same as B plus A dot B dot C same as A dot B dot C, and so on. So similarly, we have few rules. So R union S is same as S union R. R intersection S is same as S intersection R. So that means either you can say student intersection instructor or instructor intersection student. Student union instructor or instructor union student. But remember, set difference is not like that. It's not commutative. A minus B is not same as B minus A. Right? Yes, it work for here, but not for here. So then, when we have two same operator twice, we don't care which two you do first. Maybe first you do S union T and then union with R, or first union R and S and then union with T. So that is same for intersection also. So keep those in mind. Right. Now we can combine. Just like we write A plus B dot C plus D, maybe bar, then XO E or something like that. So we can now combine. But this time what we have is, for combination, what we have is union, intersection, set difference. Because projection, selection are for one thing. That one thing can be again combined thing, result of a combined thing. Just like this not is a unary operator, but this not is done to this particular block. But it must be done to one particular block. Here, one particular data set. Okay. So these are some examples. Right. So this is our requirement. Assume that we have a table called employee. Retrieve the first name, last name. You can assume that these are valid fields. And salary of all employees who work in department number 5. So if you forget about the who work in department number 5, what is your uh, algebraic, relational algebraic expression? 5 employees where, sorry, not where, I need the first name, comma, last name, comma, salary. But now we have who work in department number 5. Now I got all the employees, like details, but only these fields. But that is only part of the solution. So now I want to get only employees working on department number 5. Already I have filtered out the 3 fields. Assume there are some other fields also. Now I can say for sigma, because this is a result data set, department number equal 5. So first I do 5 and then I do sigma. And this gives you your requirement. Be satisfied, right? Because we have only these 3 fields and also only for students having employees having this department. And now you can clearly see something. Either you can write it like that, or first you can do the sigma. Filter out records, selection. And on those selected records, now you filter out the required column. So that is another option. That is another option. So therefore, either you can write like this, or you can write like this. Okay. Both are valid. Both are correct. Both are theoretically 100% correct. But if you look at practically, which one is better? Anyone? So this is my X approach. This is my Y approach. First we do 5 and then you do sigma. Here first we do sigma, then we do 5. Which approach is better according to your understanding? If you can't answer this question, you are perfectly okay. I'm just checking whether if you have learned a little bit advanced things about databases, or if you have already thought about these things seriously, then maybe you have answer. But I need a justification also. Just the answer is not enough. You must say X or Y and then Y. Practical explanation. And again, if you can't answer this, that is perfectly okay. This is I'm asking question outside what you are what you should know by now. This is just a bonus question. Anyone can give me an answer and justification. So that justification you can give if you know practically how this is done in the computer. Remember the 3-tier architecture? So we talk about this level, right? Tables and so on. conceptual layer, logical layer. But in reality, when you have a database, what you have is set of files. That is the reality. So if you go to the file level and think about how the operating system works with files, that is why you learn operating systems and so on, right? File handling. If you combine your knowledge, you should give me an answer and justify it. X because it's retrieve the F name, L name, salary of employee table, which select. Of course, you explain what you are doing. You don't justify, right? You just explain what is this query is. So yes, what is this query is? But you don't justify it. Why this is better than the other one. So when you select one from the other, you need to compare the two answers, two options and explain. Because of that, this is better. You can't just explain one side and say this is better because then you don't talk about the other side. And by the way, this is not in your syllabus, semester 2 syllabus. This is in your semester 3 syllabus, data management. Right? Justifying which approach is better. Actually, you need to decide that also. Okay. And if your data is already sorted, right, index file or something, so then actually this approach is better. Your data is already in the files, your data is sorted, maybe by department number, or there's an index for department number. So in that case, from your hard disk or SSD, if you use this approach, we can take only department number 5 employees. Maybe there are thousands employees, maybe only 75 employees in department number 5. So then if there's an index or if it is sorted by department number, your data, this query is better because then we can, from the secondary storage, we can take only department number 5 employees. And then in the memory, we can filter out other fields and take this. But if you go for this approach, the way we handle with files are, we take records record wise, not column wise. There's no way we can take data column wise. Okay. So in that case, we need to get all the records. If there are 1,000 employees, all 1,000 employees to the memory, and then filter out in the memory, which is not efficient. So therefore, in conventional database systems, this is more efficient. But there's another type of database called column family databases. In that kind of a database, even this can be done very fast. So that is all for your semester 3 database subject. Now you can see semester 3 database subject, why you have semester 3 database subject. In semester 3, we are pretty much working with physical layer. In semester 2, we are pretty much 100% in logical layer. But this is not the end of the story, right? So if you go to semester 3, you have data management systems. Right? And there you have database indexing, tuning, performance improvements. So there you are going to use these concepts. Right? You are going to use these concepts. And it's very challenging subject. Unless you have a very good foundation here, you can't do it. Right? You can't do it. You can see. So you are going to look at exactly how it is working in the computer file system. Right? Computer file system. and a lot of calculations and so on. So this is just one topic of that subject. Sometimes you might get scared also, okay.
So does this SQL?
Sorry?
Does this SQL?
No. Does this means what I am referring right now?
Yes.
No, this is a physical layer, how the data is arranged and so on. Okay. This basically physical layer, learning the physical layer, how the things are arranged. Okay. Right. So in order to understand those things, so this is the basic point. So that is why I'm doing this super slow. Super slow. Okay. So this is a very critical topic. So don't think that those subjects are difficult. Of course, those are going to be difficult if you don't understand here the basics. Right. So therefore, for your level, that means semester 2, of course, you are going to learn those things pretty soon in semester 3, in maybe 5 months' time. But until you have your exam, semester 2 exam, you don't need to worry about whether you do phi or sigma first. But always try to write sigma first, because you, in general, with normal databases, doing sigma first is more high performance than doing phi, because it's more practical. So therefore, in general, try to do sigma before phi. And most of the examples also, you will see sigma before phi. First you do the sigma and then do phi. So as a convention, just do it, because in general, that is the best way to do. But in your exams, it is not really a matter, because we don't care about performance optimization. Okay. So either you can write it in one step like this, or you can break it into 2 steps and write. So first you do the sigma and you give it a name, something like a intermediary name, like department 5 employees. So course, there's no table like that. Just you give it a name. So then on that result set, you can even call it X. On that X result set, you do the phi operation. So either you write it this way, or you write it in single step. It doesn't matter, as if you are comfortable with this step. But when you study, better to break it into steps and do it until you are comfortable. Maybe once you get comfortable, maybe you can straight away write as well. Right. So let's take another example. Retrieve the employee number of all employees. Right. Retrieve the employee number of all employees who either work in department 5 or directly supervise an employee who works in department 5. Actually, this is a very difficult one. So let's skip that for the time being, because you will get a little bit confused if you're doing this for the first time. Okay, so we will do this later, because it's a recursive one. Okay, right. I will give you a different example. Okay, I'll give you a different example. Maybe I can give you a database table first. Right, assume these are our tables. Okay, these are our tables. We have 4 tables. Employees related to department, and also projects. Employee can work for many projects. Project can have many employees. So therefore, this is the connecting table. So therefore, this relationship is something like this. You have the employee, You have the department. It is one to many. One department can have many employees. One employee belong to one department. So then you have the projects. One employee can work for many projects, and project can have many employees. Therefore, we have connecting table. Employee project. One to many, one to many. Right. So now you need, this is my requirement. This is my requirement. Remember the name is here, salary is here, department number is here. Here department number is here, primary key. This is the foreign key. Here the employee ID is there. Employee number is the primary key. Department number, department name, and location. Here project ID, project number, project name, and here of course project number, sorry, employee number, project number, and hours work. Okay, right. So my requirement is I want employees salary, sorry, names only, names, that is, say we have salary and name, right? Name. I want the name of all the employees whose salary is greater than 100,000. You need to write it as a relational algebraic expression. I need names. Assume there's a field called name in employee. Names of employees whose salary is greater than 100,000 rupees. I just need the names. Right. Write the expression. Write the expression. Okay. How do you do it? So first we'll do the sigma. Sigma from employee where salary is greater than 100,000. And then we'll do phi. We only need name. That's it. Or you can break it into 2 steps and write. You can break it into 2 steps and write. Or you can do the first 5. But if you do 5, now you're in trouble. Why? If you do write like this, what is wrong with this expression? Say 5 names, then sigma, salary greater than 100,000. Now, someone tell me this is the second approach. What is wrong with this one? Actually, this statement is wrong. You need to tell me why is it wrong. Think about it and tell me why it is wrong.
So what is sigma means here?
So sigma is selection that I already explained, right? So I already explained what is sigma, what is phi. So what is wrong with this approach, this expression? No one? So here you have taken from, of course, the table must be there, okay, employee. From employee table, you have taken only name fields. Now you have only name fields. Now, when you have only name fields from the employee table, how do you filter it? Because salary is not there, because you have taken only name. So that means then you must write it like name comma salary. So that now you have the name and salary. Then you filter out for the salary, because now you need name only, then again you need to do file, which is a headache, right? That means you first take name and salary and then filter it on salary, and then you take out the salary, keep name only. But that is unnecessarily complicated. So therefore, this is better. So therefore, when you do first five, there are practical issues also. So that means when you take out fields, if they are in the future, if you want to do some selection, you need to keep those fields. Otherwise, you can't do the selection. So that is why in general, it is better to do sigma first. In general, it is always easier and safe to do sigma unless you have very good reason, and then do phi. Okay. Right. So any questions? Because your semester 3 database subject heavily depends on this knowledge. Right. So now we move on to our next set of operations, join operations. Right. So we can identify two join operations. One is inner join, other one is outer join. Okay. Inner join, outer join. First, I will explain what is inner join is. Then I will explain what is outer join is. Okay. Right. I will come back to this theta join and equijoins later. Right. What is mean by inner join? So inner join means, say we have two data sets. They must be related. Not necessarily the same data, but related, like employee and department, student and course. Okay. So we can do joins only for related data. So inner join means we take only related data. We take fields from left table, also fields from right table, but that means we are going to combine. Remember, in Cartesian product, we just combine blindly. This with this, this with this, this with this, and then this with this. So that means each record is combined with each other elements, right? That is Cartesian product. But in inner join, we only connect related records. And when you create an inner join, you must tell which field is used to join. In Cartesian product, there's nothing called which field to join, right? Because we connect each record with each other in the other table. But here you need to specify, we do the inner join based on this field. So that is basically your foreign key. right? So therefore, this is how you specify inner join symbol, something like this. Okay. Say employee inner join department. Now you need to specify what is your joining field. That is department ID and ID. So that is employee department ID equal department's ID, right? Department.id, employee.department ID equal department.id. That is your join condition. And this specify that it is a inner join. Okay, inner join. So the result is you get this record. One Nimal Pereira, blah, blah, blah. And one Nimal Pereira is working in department 1, then HR Colombo. Two Kamal Bandara, blah, blah, blah. Again, work in HR. So therefore here HR Colombo. And Ravi Gamage, two is finance candy. And this guy is Dilini Fernando, department 3. 3 means admin goal. And this guy is not related to a department. So therefore this record is taken out. So your result has only 4 records. This is taken out because this employee is not related to a particular department. Okay. And also there is no information about marketing department because none of the employees are related to marketing department here. Therefore, you have 4 records with these fields and additional fields from this table, but the related record. That is what inner join is. Okay, so the result is something like this. So 1, 2, 3, 4 records are there, but 5th record is not there because there is no connection. And it's mentioned nothing about marketing department because none of the employees are working for marketing department. So that is what is meant by inner join. Inner join. Employee inner join department, employee.department ID equal department.id because here we call it ID or whatever the field names. Is it clear? So this is not really intersection. Not really intersection. It's inner join. It's between 2 tables. So intersection is between 2 similar things. This is between 2 different things which are related. Okay. Right. So then we'll move on to outer joins if you don't have any questions. Right. So when it comes to outer joins, there are 3 types of outer joins. What is called left outer join, right outer join, and full outer join. So left outer join, when we have 2 tables, so this is how you represent left outer join. And left side now we have open it, outer. Okay, left outer join. So left outer join means you take all the records from left table, all the records. That means in this case, if you do a left outer join, this record is also in our result because here you take all the records from left table and related field from right table. So therefore, these fields will be there, and because the last record is not related to the department, here it will be null and null. But this record is there because it's a left outer join. Left outer join. So in left outer join, if your left table has 85 records, the result also has 85 records. That is not the case in inner joins. Right? So this is our left outer join. Now you can see Ruvini Silva record is there. with other details as null. So these are the 4 fields from the department table. 3 fields from the department table. These are the fields from employee table. Okay. So you can clearly see the Rubinicil record is there because it's a left out join. Obviously, department ID is null here also. And for here, we got null, null, null. Right? Null, null, null. So that is called left outer join. Now here left right matters. So left is this table, right is this table. If you want, you can write it as other way. Then you need to adjust. You need to adjust. So therefore, in general, A inner join B is same as B inner join A. But A left outer join B is not same as B left outer join A. So just keep that in mind. Right? A left outer join B is not same as B left outer join A. But A inner join B is same as B inner join A. So now we work with data. Now we work with data, not elements. In sets, it's elements. In Boolean logic, it's true, false values. So therefore, working with records is somewhat more challenging. It's not as simple as working with sets, elements, or true, false values. So this is, you need to think a little bit more. And remember, these days we have very hot field, data science. If you want to learn data science, so this is very critical topic. So don't think that data science is for everyone, right? So you need to have this sense of data if you want to move into the data science field. ID 2 times. Yes, all the fields from left table you need to mention. Right? All the fields from left table. Then all the fields from right table. So this is fields from right table. This is fields from left table. Okay. And of course, this is a common field. So therefore, you get the same data. And some people just put it only once, especially if the name is also the same. But the best practice is put it twice. Put it twice. Okay. Because sometimes the name is also different. But obviously, these values are going to be the same because effectively these are the same. But this is coming from employee table. This is coming from department table. Right. So that is called left outer join. So the next one is right outer join. So now you can see right side we have opening. We have opening in the right side, not the left side. So that is why we say left right matter now, right? So this is my right side. So this is how you get right outer join. You take all the records from the right table. Okay. You take all the records from right table and relate it with the left table. Relate it with the left table. And if you have a record in the right table which is not related to left table, you only show the right table fields. Now this is driven from the right table now. Right table. So let's get back to our original tables. Say I want employee right join department. Right. Employee right outer join department. based on obvious department ID and ID. Okay. Now you drive from right side because right outer join. Therefore, it is 1 HR Colombo. Then you need to find out which employees are in department 1. 2 employees. So then 1 Nimal Pereira, blah, blah, blah. That is, you join this with this guy. Then you need to join this with this guy also. Then again 1 HR Colombo. Then again 1, 2 Kamal Bandar. So this is 1, 1, okay? 1, 1. Then 1, 2 Kamal Bandar and blah, blah. And that's it for 1. Then 2 finance Candy. Then see which is connected to 2. This guy. That is again 2. Right? 2. That is 3 Ravi Gamage. 3 Ravi Gamage. Then take 3 because that's all. Then 3 admin goal. Then see who is connected to 3. Only 1 record. That is again 3. And then 4 Dini Fernando and so on. And then you have this record. 4 marketing Gampaha. But there's no record related to 4 marketing department. So therefore, here you just say null, null, null. Only once. Null, null. And that's it. That's it. Okay. And now you can see this record is missing. So none of these record mention about 5 Ruvini Silva. Because we drive it from right side. It's a right out join. So therefore now I have 1, 2, 3, 4. 4 records. Sorry, not 4 records, right? 1 and 1, 1, 2, 3, 4, and 5 records. Because this is also record. I have 5 records now. For the 5th record, you don't have the employee details, all are null, 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 null. But none of the records refer to Ruvini because Ruvini is not belonging to any of the department because we drive it from department side. Okay, so that is how the right outer join is done. So the result is this. Of course, we have taken the employee details to the left side, right? But this is your last report. 4 marketing Gampaha, all are null. And you can see none of the records referring to Ruvini Silva because Ruvini Silva is not assigned to a department. So you can see no record related to Ruvini Silva here. That is called right outer join. Okay. So then final one is full outer join. So full outer join is left outer join union right outer join. So whatever the records you get it in the inner left outer join must be in your final result. Whatever the records you get it from the right outer join must be in the final result. But if the same record is in both results, you take it only once. So that is, you are going to have the common records plus in your full outer join, you are going to have this record. That is employee without department. And you are going to have this record also, that is department without employee, because it's a union of both. So that means all the related employee details and employees without department records and department without employee records. All those must be in your full outer join, but none of the records are duplicated. So this is the result. So these are coming from inner join. This record coming from left outer join, this record coming from right outer join. Sometimes multiple records maybe they are in left outer join and multiple records coming from right outer join as well. Is it clear? Is it clear? Because this is you are working with data sets now, not true false values, not numbers. This is not normal algebra. This is not Boolean algebra. This is not set algebra of sets. ඔයගොල්ලෝ කොච්චර algebra දන්නවා කියලා ඔයගොල්ලෝ හිතනවා. ඉස්සර දන්නේ මොනවාද? නිකම්ම algebra. Algebra of data numbers. Right. X squared minus y squared. ඊට පස්සේ ඔයගොල්ලෝ ඉගෙන ගත්ත මොනවාද? Algebra of sets. Right. A intersection B same as B intersection. And the De Morgan rule. A intersection B complement is A complement union B complement වගේ. Right. A intersection 5 is 5. So then you learn Boolean algebra. Right. A dot B. Sorry. A dot B plus C is same as A dot B plus A dot A. A dot B plus A dot C. And so on. So now we are learning relational algebra. Algebra related to data. ඔයගොල්ලෝ මීටරේ දැන් මේ විදිහට සෑහෙන හොඳට වදින්න ඕන හරි. IT කරනවා කියන්නේ මීටර. ඒක නයි කිසිසක් කියන්නේ හරි. IT කරනවා නෙමෙයි IT හරියට ඉගෙන ගන්නවා කියන්නේ සාමාන්‍ය මිනිස්සුන්ට වඩා පට්ට මීටර. IT කරන අය කොහෙන් හරි ගොඩ යනවා බොහෝ වෙලාවට. හරියට කරන කට්ටිය. මොකද අනිත් අයට වැඩිය මීටරේ හොඳයි. මොකද ඕගොල්ලෝ සාමාන්‍ය algebra දන්නවා, algebra of sets දන්නවා, boolean algebra දන්නවා, relational algebra දන්නවා. functional dependencies හොයන විදිය දන්නවා. අරක කොහොමද මේකද depends උනේ කියලා. තව ටිකක් ඉගෙන ගත්තොත් එimhe තව දේවල් ඉගෙන ගන්නවා. තවත් ටිකක් උඩට ඉගෙන ගත්තොත් එimhe AI ඉගෙන ගන්නවා. කොහොමද කම්පියුටරේට බුද්ධිය දෙන්නේ කියලා. සෙල්ලන්නේ නැහැ. සෙල්ලන්නේ නැහැ. අනිත් මිනිස්සු කරන ගොන් වැඩත් එක්ක බැලුවා. බහුතරයක් කරන ගොන් වැඩත් එක්ක බැලුවා. හරියට කරගත්තොත්. Right. So now we move on to our final operator, division operator. So this is a little bit more complex. Right? You need to think a little bit more seriously. So therefore, we have taken a very simple data set here. So this is one table or data set. Okay. This is another data set. And now what we are going to do is this data set divided by this data set. So it's something like 10 divided by 5, which is 2. Right? 12 divided by 4, which is 3. Of course, this division is not same as this, but the concept is coming from somewhere from here. Arithmetic division. And there was no division in sets. There was no division in Boolean algebra. But there's a division in relational algebra. Now with I division come with. Right. What is mean by division operation in relational algebra? If you have x squared minus x divided by x, what is the result? You can take the common things, right? X taking it out, then x minus 1 divided by x. Then you can say, then තමයි ඔයාලට බෙදා ගන්න පුළුවන්. බෙදා ගන්න පුළුවන් වෙන්නේ මොනවා වුණොත්ද? common දෙයක් තියුණොත්. right? ඇත්තට මේක ලියන්නේ කොහොමද? බලන්න හරියට කතන්දරේ තේරුම් ගන්න. So 10 is 5 into 2 divided by 5. common දේ තමයි මේ කපලා දාන්නේ. පේනවද? බෙදනවා කියලා කරන්නේ මොකද්ද? ගුණිත වගේ ලියලා common එකට කපලා දානවා. දැන් ඔයාලට බෙදනවා කියන්නේ මොකද්ද කියලා සීරියස්ලි කල්පනා කරන්න වෙනවද ඉතලා. මොකද අපි නිකන් ඔහෙ බෙදනවා කියලා ඔහෙ බෙද ඉන්නව නේද? එච්චර සීරියස් ඉදලා. common එක අය තමයි මේ කපලා දාන්නේ. So here, division is not exactly the same concept, but something somewhat similar to that concept. Somewhat similar to that concept. Right. So let's see what is meant by division. So now we have two tables, right? Completed table, database project or DB project table. So what is mean by completed divided by database? So that means you take one record from here and see whether no, you take from left side, not right side. You take your first record. Assume this is your primary key and see whether it is related to the first record here. Yes, database 1, database 1. Then see whether the same student is related to the next one. Yes, Fred is related to database 2. So that means this is common. That means Fred is doing both database 1 and database 2 tasks. It's a common guy. If it is a common guy, you take it to the outside, resource set. And of course, Fred is doing compiler 1 also, but we don't care. ඒක හරියට අර මෙතන x වර්ගයේ ඍණ x ගේ x එළියට ගත්තට පස්සේ x ඍණ 1 කියලා ලියලා x ගත්තා. ඔව් මේ මෙතන තව මොකක් හරි දිනවා ඒක අපිට අවුලක් නැහැ. හැබැයි අපිට මේක බෙදා ගන්න මේ ඇති. Therefore, we don't care about Fred doing compiler 1. But Fred record is common to both all the records here. So therefore, we take Fred. අර x ගත්තා වගේ x බෙදුනා වගේ. So then you don't care about this because this is not related to data, any record here. Then Eugene, database 1, okay, but Eugene is not connected to database 2. So therefore you don't take. That name is not in the result because it must related to all the records, not just one record. So therefore we don't take. Then Sarah, yes, connected to database 1, connected to database 2. So you can take Sarah. So that is how you take it. So you take record from left side and see whether it is related to all the records in the right side. Then you take that record. Otherwise, don't take. Okay. Right. So this is the easier one. Forget about this. Right. You need to do R divided by S. Write down R divided by S. Of course, this is the answer. I just shade it. So that means you need to take a value from A because A is the common field. And see whether is it related to all the records here. If it is related to all the records here, you take it. But if it is not related to all the records here, you don't take it. What is the result? R divided by S. Result is B1 and B4. Why? You can see that B1 is related to A1, A2, A3. Yes, you need all three. Right? B1 is related to A1, A2, A3. Then what about B2? B2 is related to only A1 and A3. So therefore you can't take B2. Then what about B3? B3 is related to A2, A3, A4. A2, A3 is there, but A1 is not there. We don't care A4 because A4 is not here. So therefore you can't take B3. And what about B4? B4 is related to A1, A2, A3. All are there. So therefore, you need to take B4. So you need to take B1 because it's related to A1, A2, A3. You need to take B4 because it's related to B1, B2, B3. A1, A2, A3. Obviously, you can't take B2 because it is related to only A1 and A3. You can't take B3 because it is not related to A1, though it is related to A2 and A3. Right? So that means you need to check whether it's common. It's something like common factor. Right? Common factor. If it's related to all the records in the right side, you take it. Otherwise, don't take it. Okay, actually, these two records columns must be other way. B here, A here. Because A is the common field. B is what we are looking for. Okay, so this little bit confusing. Actually, we should have drawn it B here, A here, because I just took it from different book. Okay. Okay. Now, if you take this example, now see whether you can look at it in practical manner. Right? Look at it in a practical manner. Say this is my employee table. I have employee 1, employee 2, employee 3. Other fields I have not shown, right? And then I have employee project table. Employee project. Then I have the project table. And project I have P1, P2. And this is my employee project. I just show you the primary key and maybe number of hours. Employee 1, project 1, say 12 hours. Employee 1, project 2, 5 hours. Employee 3, project 2, 8 hours. Employee 3. Employee 2, project 2, 4 hours. And employee 2, project 1, 8 hours. I need employee divided by employee project. Which records will be there? So employee 1, project 1, employee 1, project 2, employee 3, project 2, employee 2, project 2, employee 2, project 1 is there. Basically, try to understand what is mean by this and put it into simple English. What is mean by employee divided by employee record? Put it in simple English.
Sir, can you repeat it again?
So these are my employee records. These are my project records. And this is my employee project records. That is because it's a many-to-many relationship. These are the records E1, P1, 12, E1, P2, 5, E3, P2, 8, E2, P2, 4, E2, P1, 8. My question is, which records will be there employee divided by employee project? This divided by this. First, I need a simple English expression that explains what is this. What is the purpose of this? Otherwise, you just like a machine, you do it without knowing what you are doing. So in simple English, because no one gave me answer, employee divided by employee project is employees who are working for all the projects. So if there's an employee who is working for all the projects, we take it. So employee 1 is, there are only 2 projects working for project 1 and project 2. So therefore employee 1 is taken. Employee 2 is working for both project 2 and project 1. We take employee 2. Employee 3 is working only for project 2. So therefore you don't need to take employee 3 because employee 3 is not such an employee. So when you divide, you will get only employee 1 and employee 2. Because those are the employees who are working for all the projects. How do you know all the projects? Because project table has only 2 projects. So that is what is meant by division. Okay. So there can be such requirements. There can be such requirements. ඔක්කොම projects වල ඉන්න employees ලා ඉන්නවා. ඔක්කොම departments වල මේ දවස්වල මේ වෙනකොට වැඩ කරපු employees ලා ඉන්නවා. If you are the historical data. ඔය කියන ඔක්කොම task කරපු අය ඉන්නවා. task පහක් තියෙනවා. පහම කරපු අය ඉන්නවා. මොකද ඒගොල්ලෝ වෙන වෙනම records වල තමයි වැටලා තියෙන්නේ මේ task එක කරා මේ task එක කරා කියලා. දැන් ඕන ඔක්කොම කරපු අය ඉන්නවාද කියලා. So that is where we use division operator. Right. Right. Now I'll get back to few more things. Now the important thing is done. Important thing is what is inner join, what is left outer join, what is right outer join, what is full outer join, and what is division. I will now explain what is mean by equijoin and theta join. So equijoin means whatever you join, inner join or outer join, if the join is based on equality, like this table's employee department ID equal that table's department ID. This table's employee ID equal that table's employee ID. I think this is also not correct one. So this should be not employee ID. You can see this is a little bit erroneous examples are there. That is why I want to give you new one. So because this doesn't make sense. Right? Employees department ID equal department ID. So if you have equality, we call it a equijoin. Of course, your inner join can be equijoin, left outer join, right outer join, full outer join can be equijoins. So because this is a different concept. So basically all the examples we discussed so far are equijoins. All the examples we discuss, we use equal mark. So then we have theta join. Right? So theta join means it's a general concept. So it can be either equality or inequality. So therefore, equijoin is a special case of theta join. Theta join is a general case. Okay. So equijoin is a special case of theta join. Because when you join things, we can even use less than or equal, greater than or equal. If it makes sense, it doesn't mean that this always makes sense, but sometimes it makes sense. Okay. Like salary or something, it makes sense. But for department number, usually it doesn't make sense, right? Whether your department number is bigger than the other department. But if there's a ranking, order by some concept, maybe yes, like you want to check whether people who are in higher rank than you in army or something. So then it makes sense to do a theta join. Maybe you are colonel, so your rank and above officers. Maybe you can do a theta join because equijoin means something else. Okay. So this is an example for theta join. Okay. So look at this. It's an inner join, but it's not an equi-inner join. It's theta inner join. Okay. So car inner join with board, condition is car price must be greater than board price. Okay. And if you do a equi-join here, actually nothing will be there, right? Because now you do the join based on price. This is our common field. So 20,000, no 20,000 here. 30,000, no 30,000 here. 50,000, no 50,000 here. Actually, if you do a equi-join, you will get no records. But now, so that means equi-inner join. But now what we are doing is theta inner join based on this condition. Car price must be greater than or equal to board price. So that means you need a car price which must be bigger than the board prices. Then you join it. So 20,000 is bigger than 10,000. So therefore we have car A 20,000, board 1 10,000. That is this record. Then take car B 30,000. So this must be bigger than this. Again, we can join it only to this one because 30,000 is bigger than 10,000. So car B 30,000, board 1 10,000. Now if you take car C 50,000, 50,000 is must be bigger than this. Of course, 50,000 is bigger than 10,000, 50,000 is bigger than 40,000. So therefore I can connect car C 50,000, board 1 10,000 and car C 50,000, board 2 40,000. So this is the result. This is the result of the theta join. Okay, this is the result of the theta join. Is it clear? It's an inner join, but theta inner join, not equi inner join. So this can even be a outer joins. Okay. Right. So that is equi join versus theta join or conditional join. Already we have discussed what is inner join, left outer, right outer, and full outer. This is a different classification. This is another classification, but this is the most important classification. So then we have another special type of join called natural join. So this is completely different story now. Right? This concept is independent from whatever we have discussed so far. So natural join means it's an implicit join. So if the two tables that you are going to join has a common field name, like department name, the field name is the same, then you don't need to specify what is your equijoin. If you don't specify what is your, because when you are doing a join, you need to say that this table, this field is say, connected to the other tables, this field. But if you have the same name, we can assume that, but make sure you have only one such column in each table. So then you can assume that that is your common field and it's a equijoin. And if you write it under that assumption, we call it a natural join. But very rarely we do that because it's always good to specify it, right? But if it is not specified, see whether is it a natural join. See whether there are two common field in both tables. So then just assume it's a natural join based on that field and it's a equijoin. Okay. So that is called natural join. Okay. Natural join. And natural joins are usually inner joins. But if you want, you can write a natural joins, which is left outer join, right outer join as well. Okay. So basically natural join means we use the common field, right? We use that common field, though we have not specified. Okay. Right. So now we have all the classifications: inner join, left outer join, right outer join, and full outer join. Then equijoin versus theta join. Equijoin means equality mark. Equality is used for your join, whether it's inner, left outer, right outer, or full outer. In theta join, it can be equality or comparison. Greater than is greater than, no equal is less than is less than. So theta join is the general concept. Equijoin is a special case of theta join. And natural join means you join based on that common field, the field having common name. And it can be again any of those joins. Right, so I have given you some examples. Actually, those were there in your UCSC VLE some times ago. You can do it by yourself. Right? You can do it by yourself, and we will be doing some past paper questions as well later. So when you have 2, 3, 4 tables, things can be really challenging. Okay, really challenging. And usually your exam questions are very challenging. Okay, so shall we do a past paper question? By the way, now we have done with relational algebra. Just 2 more topics. Okay. So there are some past paper questions. It looks like near impossible. Very difficult to think. But don't worry, you don't get all the question like that. Okay. Right. Try to do this one, fourth one. This is last year paper. Which of the
So only
following
one.
option correctly provides relation that includes all the books and articles authorized by Asanka? I hope authored by, not authorized, authored by Asanka. And you can assume that there's a table called books, there's a table called articles. Of course, they don't use that kind of thing. They assume that you have the common sense to think like that. Right? Quickly do it and give me the answer. Is it multiple answers possible? No, only one correct answer. So that means it's only one correct answer. Now, this one is really confusing one for me also because it looks like the examiners use little bit non-standard terminology. So remember, we never discussed something called plus. I don't know whether you use examiners use plus for the union. Okay, plus for the union. But plus is not usually used. I have not seen it. Okay, but anyway, because it can't be this Cartesian product, right? You connect all the books with all the articles. Say you have book table, say book ID, book name, author name, and then the article table, article ID, article name, again author name. So you are supposed to work with author name field. You can assume that author name is or author field is common in both tables. So I don't think this is an answer. So this is sigma from here use. That means these are the books. From books you subtract articles. I don't know. It doesn't make much sense to me. What is mean by from books subtracting articles? I'll not take that. This is you're taking only the field 5 author. Now you can't write like this. If it is 5, you can't have author equal. If it is 5, you just say author. So therefore, this is wrong syntax also. For sigma only you have this. For 5, you just say what is your field. Anyway, this is okay. So this is also wrong anyway, because it says author equal Asanka. So for 5, you don't have something like that. 5 means just author, comma, this. Anyway, syntax is also wrong. Here syntax is also wrong. So therefore, I can take out ABC. Now this is Cartesian product, right? Books, all the books records connected with all the articles records. So then you filter out where author is Asanka. So this is not the very good way to do it, but this really work. This should work, though it's very inefficient way to do it, because ultimately you filter author equal Asanka. So therefore, I don't know whether this is the best way to do it, but it work. It should work. Now, this is actually they should have done sigma author Asanka books, sigma author Asanka articles, and take the union. Take the union. I don't know whether the examiner referring to this as union. So therefore, this is little bit non-standard expression, right? Non-standard expression. So therefore, I'm reluctant to go for this. I don't know whether this is another operation, but I have I have never seen this kind of operation in your past papers. So therefore, I'm a little bit reluctant to go for that, but I don't know whether the examiner will take, but definitely not ABC. Still, I will go for D because this is little bit non-standard notation. Okay. I don't know if the examiner go for E, but I will go for D for the time being. Right. Let's look at the answer. Question number 4, right? Yes, examiner has taken D because this is not a standard operation. This is not a standard operation. So the examiner has taken D, right? Because we never learned something like this. Okay. Right. So you can see that is the expectation, right? That is the expectation. Do you have any sigma example? Yes, we have more examples. So these are somewhat challenging, definitely somewhat challenging. Usually sigma 5 questions are very challenging. Right, so shall we do this? Or is it too difficult for you? I don't know. Always, right? मेरे question එක ගත්තත් ඔය වගේ තමයි. හරි කල්පනා කරලා කරගෙන සමහරට මටත් ඔළුව කැක්කම හැදෙනවා කල්පනා කරලා. කමන්න කරමු. Right, so let's do the 35th one. You can get the past paper from your VLE or our Google Classroom. This is 2023 paper, okay? So you must have the past paper with you. Consider the following two relational schemas. Works, lives. Which of the following relational algebra queries will give you the name of the employees who work for department ISC along with the cities where they live? Which of the following relational algebraic expression query will give you the names of the employees who works for department ISC? That means department name must be ISC. Along with cities where they live. So I think that is not very difficult one. Right? So you need to give the name of the employee and their city, but only those who are working for ISC department. I think that is not difficult. I thought it's a difficult question, but it looks like not very difficult, but I don't know whether the examiner is going to take it in a very complicated manner. You can take it in a very easy manner, but maybe the examiner is taking the answer from very complicated manner. I don't know. Just do it and see. Just take one by one and eliminate wrong answers. What is your answer? Remember the city is in the lives table. So therefore, yeah, I am not going to tell anything. So you need default employee's name. and city where that employee lives. But only for employees in ISC department. Is it A, B, C, D, or E? So remember only one answer, correct. Right. Anyone? E. So two different answers. One says B, another one says C. Any other answer or same answer? So one answer is B, one answer is C. So this paper only one answer, it must be correct. Anyone? අනිත් අය හිතා ගන්නවද බැරිද? Okay, so let's see. Let's see with the first one. What about the first one? So from works table, you filter out records where the department name is ISC. That is okay. And you take only employee name. So that is not going to work at all because now when you have only the employee name, there's no way you can join it. Because you can join using, no, you can join using employee name. Right. So therefore that is also fine. So now you have all the employee names who are working for department ISC. Right. Now you do union. So union is not going to work because union means common fields. Right. Common fields. But sometimes for this one union might work. If the same name is there, you take it. But ideally it should be a join. So these are not union compatible also. These are two different tables. Right. I don't think these two tables are union compatible because this is work table, this is lives table. I'll not go for this. If I have no other option, I might come back here. Right? Because this is not the standard way. Here, usually we need to go for a join. Right? What about this? You get all the employees who are working for ISC and they are only employee names. Okay? Employee name. And here also we have the employee name. It's a one-to-one relationship. Right? Because it's a one-to-one relationship, this might work also. But anyway, let's keep it for the time being. Right, what about this? Then you join with lives, but they have not mentioned using which field. Maybe you can assume it's a natural join then, because employee name is a common field. That is why I explain you what is natural join is. Common field that natural join and it's an inner join. And then you take the employee name and city. That looks okay for me because already we have the employee name. From here, you get these three fields and you don't need street. So you just take the employee name and city. So this looks okay for me. We'll see. What about this? From works table, you filter out the employees, but this is 5. 5 you can't write like this. Okay. So therefore, I will not take this. So department name is ISC. You take only employee name, fine. Like employee name. So then You join it with lives. Let's assume it's a natural join. We call it R2. From there, we take employee name. Is it same as this? Wait a minute. Phi employee name, sigma department name works. These two are the same. This is Cartesian product, not a join. So therefore, we will not take this because this is not a join. This is Cartesian product. So this combine all the possibilities. I will not go for this. So from works, you filter out only department employees, their employee names, and then we intersect with lives table. Intersect. Intersect means common. So because it's one-to-one, this may work, but these are not compatible. These are employee names, these are some other fields. So therefore, though it looks also okay, but this is not the standard way to do it. Sometimes this might work because it's a one-to-one relation, but these are not compatible. It's like intersecting apple with orange. So therefore, anyway, I will not go for that. Okay. So these two may work, but not the best. In this special case, it may work, but I will go for B. Because that is the standard way of doing. Right. So let's see what is the answer for 35. Is it B or something else? Yes, it is B. So the standard way is doing the join. Okay. Standard way is doing the join. Right. So I hope now you have an idea about what kind of questions you are getting. Okay. What kind of questions you are getting. Right. So there are some more questions. Okay. Some more questions. Right. So you must try out those. Try out those. Okay. You can see join, then sigma, then phi, and blah blah blah. Right. It's a very important skill. Right. So usually I take more times for very critical skills for your life, like Boolean algebra, relational theory, functional dependencies. So usually I don't take much time when you are doing HTML, CSS, JavaScript. Who cares? බූරුවෙක් උනත් උගන්නන්න පුළුවන්. හරි බූරුවෙක් උනත් පොඩ්ඩක් ස්මාර්ට් නම් උගන්නන්න පුළුවන් HTML, CSS, හරි Java පවා නේද? basic Java. මේව තේරුම් ගන්නවාට හොඳ මීටරයක් තියෙනවා. ඔයාගේ මීටරේ තමයි මේ ඉම්ප්‍රූව් කරන්න හදන්නේ. එතකොට ඔයා මීටරෙන් ජීවත් වෙනවා. සමාජයට ගියත් ඔයා data records හරියට ෆිල්ටර් කරලා ගන්නවා. මිනිස්සු කියන බයිලා අතරතුර අවශ්‍ය දත්තේ වාට ගන්න පුළුවන්. මිනිස්සු බයල් බයිලා ගන්න. Right. So we'll take a small break. After the break, we'll move on to now we are done with relational algebra. We'll move on to maths. Okay. එතන relational algebra මෙතන තියෙනවා relations and functions. හරි වර පේනවා නියම. මේක එකට ගැට ගහලා තියෙන විදිය. Right. So after the break, we'll do relations and functions. And possibly we can finish it today. Right. Relations and functions. Right. So let's move on to relations and functions. Right. So in the last class, we start discussing what is relation is. Still, we have not started functions. So relation is a connection between two or more entities. But we only discuss about binary relations, connection between two entities. Okay. So we discuss how to represent a relation. We can represent a relation using algebraic expression like y equal x, y equal x squared plus 2. Or we can show the mapping, right? Domain to the range. Or you can show the ordered pairs, set notation. Or you can graphically show how it looks. Okay. So then we discuss what is meant by domain, range, and codomain. So domain is all the possible map to values, sorry, map from values. Domain. Okay. So I think I have established. So that is domain. All the values that go into the relation. So then we look at what is range is. Range is, so there's a connection between codomain and range also. Range is what actually come out when you enter any values from domain. Codomain is your expected outcome. Expected outcome is codomain. Range is your actual outcome. Domain is what comes into the what goes into the relation. Okay. So your range must be inside codomain. So it must be a subset of codomain. Otherwise, you have not defined your codomain properly. Right. So we discuss all those things. Remember, the domain is a subset of your set A. Range is a subset of your set B. Maybe you can take B as your codomain. And relationship or relation is a subset of A cross B. Because Cartesian product has all possible connections, but our relation is based on some concept. Right. So then we look at what is one-to-one relation, one-to-many relation, many-to-one and many-to-many. Right. So here we look at one-to-many and many-to-one as two different things because left-right matters, unlike the database tables. So then we moved on to special types of relations. Reflexive relations, symmetric relations, transitive relations, and antisymmetric relations. And if a relation is reflexive, symmetric, and transitive, we call it equivalence relation. Then we can write the equivalence classes for each and every value in the domain. So then we look at what is meant by partial ordering relation. So partial ordering relation means a relation is reflexive, antisymmetric, and transitive. If it is reflective, symmetric, and transitive, equivalence. Reflexive, antisymmetric, and transitive, it is partial ordering relation. That means whenever there's A to B, there must not be B to A. But at the same time, it must be reflexive and transitive. Transitive means when there's A to B and B to C, there must be A to C. Right, so that is where we stopped. Right, so now we move on to inverse of a relation. So whenever there's a relation, there's inverse of a relation. So every relation has an inverse. So inverse is something like undo. If relation is doing, inverse is undoing. If relation map A to B, inverse relation must map B to A. Okay. For each and every value, inverse relation will map it in the opposite way. Again, you need to understand it in a very serious manner. Say this is my relation R. And this is my inverse relation R, noted by R minus 1. That you can say if there's A1 to B1, inverse you must have B1 to A1. If there's A2 to B1, inverse you must have B1 to A2. If there's A3 to B2, there must be B2 to A3. If there's A4 to B3, there must be B3 to A4. Okay. And if there's A1 to B4, there must be B4 to A1. Yes. So when there are X to Y, here there's a Y to X. So therefore, definitely R inverse, this is R inverse. If there's at least one missing or at least one additional thing, for example, there's something for this, so then this is not the inverse because there's B to A1, but there's no A1 to B2. Without A1 to B2, if you have B2 to A1, this is not inverse relation. And when there's A2 to B4, if there is no B4 to A2, if this is not there, again it is not inverse. So inverse means you must have exactly the same opposite things, nothing more, nothing less. Nothing more, nothing less. Then only it is inverse. Okay. So why inverse is important? Because we need to do undo things. We need to undo things. Reverse thing. It's transaction and reverse transaction. This is the formal definition of inverse relation. Formal definition. So you must be able to give formal definition. That is one of the competency. So then you are an abstract thinker. If there's a relation A to B, where A from capital A set and B from capital B set, then the inverse of R denoted by R inverse is given by B to A, where A to B is in relation. Whenever A to B is in relation, all your B to A create your inverse relation. So that means if there's 3, 5, in your inverse relation, there must be 5, 3. If there's 2, 4, in the inverse relation, there must be 4, 2. And if this is R, this is your R inverse. Okay. So express something like this is super important because remember, programming is express yourself, right? Program කරනවා කියන්නේ තමන්ගේ ඔළුවේ තියෙන එක කියනවා. Computer එක. Communication. Programming කරගන්න බෑ කියන්නේ communicate කරගන්න බෑ. තමන්ගේ එක්ක තමන්ගේ ඔළුවට logic එකක් නැහැ. එක්ක එන logic එක communicate කරගන්න බෑ. Programming බැරි නම් වාට කරන්න තියෙන එක්ක logical thinking හදාගන්න solution build කරන්න පුරුදු වෙන්න. එහෙම නැත්නම් ඊට අමතරව එන solution එක communicate කරන්න පුරුදු වෙන්න. So then you are a programmer. Right, some properties of inverse relation. So inverse of inverse is the original relation. That is obvious. Because if A is mapped to B in the inverse, B is mapped to A. If you take the inverse of this one, again, A is mapped to B. So that means you are getting the original one. Of course, that happened for each and every. So therefore, inverse of inverse is the original relation. So that you need to think and justify yourself. And obviously, domain of the inverse relation is the range of the original relation. Because this domain is previous one's range. Your new inverse range is domain of the original one. So the range domain of the inverse relation is the range of the original relation. Range of the inverse relation is the domain of the original relation. So that you need to notice. Okay, notice it. Right, how do you find the inverse of a relation? Of course, if you have the ordered pairs, it's super easy. Say this is my relation. So what is the inverse relation? You just write the ordered pairs, but swap x and y. 2, 3 become 3, 2, because 2 to 3 means inverse relation 3 to 2. 2, 9 means 9, 2. Okay. 3, 3 is 3, 3. If you have 3, 3, of course, I have forgotten to add 3, 3 here. And 3 minus 1 means minus 1, 3. 4, 0 means 0, 4. So let me add 3, 3 here. I have small typing mistake. So there must be 3, 3 here. Right, now it is correct. I'll add the updated one, okay? Right, now it's correct. So here we have 3, 3. So therefore in the inverse also we have 3, 3. But other things, 2, 9 become 9, 2. 3 minus 1 become minus 1, 3. And if you If you are given the mapping, you can write the mapping of the inverse. If you are given the ordered pairs, you can write the ordered pairs of the inverse. Even a kid can do it. So then how do you find it algebraically? Maybe you are not given the ordered pairs. Rather, you are given algebraic relation. Something like, say, fx equal x plus 3. So what is f inverse x? Or if this is r, x plus 3, what is r inverse? So for simple relations, it's very easy. How do you do that? Say this is your relation. We will write it as y equal to x minus 1. And you remember this is called independent variable. This is the dependent variable. Or you can call it fx. Fx or gx or whatever, hx or. So now you want to find the inverse of this relation. So what you need to do is now you isolate x. Now here we have isolated y. Now you isolate x. Say 2x equal y plus 1. Then divide by 2. Half of y plus 1. Now you change it because usually we write it as y equal relation. So now swap x and y. Y equal half of x plus 1. And this is your inverse relation. And if this is your r, this is your r inverse. Okay. Simple as that. If you want, you can double check. Remember, the inverse will do the opposite. If you add 5 here, it will be 5 into 2, 10, 10 minus 1, 9. Now for this one, if I add 9, I must get 5, if this is the inverse. And if I substitute 9 here, 9 plus 1, 10, 10 divided by 2, 5. Yes, 9, 5. So when there's 5, 9 here, there's 9, 5 here, because this is the inverse. Okay, simple as that. So let's take another example. Can you find the inverse of this? Say y equal 3x plus 2 divided by 5. Find the inverse. If this is your r or fx, find r inverse. What is the answer? You can just write to inverse function also as y equals r. Anyone got it? So your new function or new relation must do the reverse of the original relation. So your task is isolate x. So I'll write it as
5x.
5y equal 3x plus 2. So then I'll write 3x equal 5y minus 2. That means x equal 1/3 of 5y minus 2. That is inverse. Right? 1/3 of 5y minus 2. If you want to double check, of course you don't need to double check, right? But if you really want to double check, say when x is 5, 5 into 3 is 15. 15 plus 2, 17. 17 divided by 5. So that means here, if I add 17 divided by 5, I must get 5. Let's see. 1/3 of course, you can write it as y equal 5x minus 2, okay? Now 5 into 17 divided by 5 minus 2. 5 into 5 get cancelled. 17 minus 2 is 15. 15 divided by 3 is 5. Yes. 17 divided by 5 to 5. Yes. If 5 to 17 divided by 5, 17 divided by 5 to 5. because this is the inverse. Y equal 1/3 of 5x minus 2. Because usually we write it as y equal something. Okay. Right. How do you find it graphically? Maybe you are given the graph of the relation. Graph of the relation. Maybe this is the graph. So you are supposed to draw the inverse relation. It's very easy. Take the y equal x line. Y equal x line. That is 0, 0, 1, 1, minus 1, minus 1, 2, 2, and so on. And draw the mirror image of your graph, taking y equal x line as the mirror. And that is your inverse. So it will be something like this. Okay. So if you know the graph, just draw the y equal x line and draw the mirror image. That is your inverse. If this is your R, that is your R inverse. Say this is your graph. Then what is the inverse? Draw y equal x line and draw the mirror image. And this is your inverse. Okay. So you need to do a little bit of experience with this. නිකන් කවුරුවක්වත් කියන පළියට විශ්වාස කරන්නත් එපා. So you can go to something like GeoGebra or any other graphing tool. GeoGebra is the most famous. GeoGebra. GeoGebra graph, yeah, GeoGebra graphing calculator. Say I have y equal 2x plus 3. Now I will draw y equal x line also. Y equal x. Okay. I will ask you to draw maybe something like this. Right. So now what is the inverse of this? Inverse of this. So let's find the inverse of this. Y equal 2x plus 3. Y equal 2x plus 3. 2x equal y minus 3. X equal half of y minus 3 or half y minus 3 by 2. So let's do that. And it must be mirror image here. So what is the mirror image here? Something like this. Something like this. Okay, let's see whether that is the case. Y equal half of y minus 3. Y minus 3. Sorry, not this. Half of y minus 3. Uh, 2x equal y minus 3. X equal half of y minus 3. So this must be x. Right. You can see that is mirror image. So that is your mirror image. So this line is mirror image of this line. And this is y equal 2x plus 3. And this is y equal half of x minus 3 because this is the inverse. So inverse is the mirror image on this. Okay. And there are some interesting mirror images. So inverse functions. Can someone tell me a famous relation and its inverse relation? Not like a straight line or something. That you must be able to give me the name also. What is the name of relation and what is the name of the inverse relation? Anyone?
So can you repeat the question?
Can you give me a name of a famous relation and its name of its inverse relation? I need two answers. Name of the relation and name of the inverse relation. My question is that. So if you take exponential function, like y equal, say, 5 to 10 to the power x, y equal 10, how do you get exponential? Using the hat character. Okay, hat character is there in your keyboard. 10 to the power x. Okay. Now what is the inverse of this? So let's do y equal x line first. And the inverse is log function. The inverse of exponential function is the logarithmic function. So therefore this is y equal log 10 x, okay, log 10x. You can see that this is the y equal log 10x, right? So it is the mirror image of this. It is a mirror image of this. So that is another reason why you learn about logarithmic function, log, right? Because log is the inverse of exponential. Okay. So likewise, the inverse of sine is called sine inverse, cos inverse, tan inverse. So those are all inverse functions. But this is the most famous one in maths. Okay. So these are some examples. So it's just you need to see the mirror image. As පේනවනම් අඳින්න පුළුවන්. as පෙනීම තියෙන විතරයි වෙන්න ඕන සම්මිතික බව පේන්න ඕන. So this is original relation and this is the inverse. බලන්න මේක පේනවද කියලා. මේක නම් ඩක් දාලා පේනවා. මේක ලේසි. මේක ටිකක් හොඳට කල්පනා කරොත් හරි. මේ කැලේ තියදලා තියෙන්නේ මේ කැලේට. මේ කැලේට අදාළ මේ කැලේ. එහෙනම් මේ කැලේට අදාළ මේ කැලේ. අන්න මේ කැලේ කැලේ කල්පනා. So therefore, if this is your original function, like y equal x squared, this is your y equal root x. If this is 10 to the power x, this is log 10x. Okay. And this is a funny guy, where its inverse is also itself. තමන්ගේ inverse එක තමන්ම වෙන function එකක් තමයි මොකද්ද? 1 over x. අනිත් පැත්තෙන් 1 y equal x. So if you take y equal x line, its inverse is also y equal x line. There's another such a guy. If y equal 1 over x, its inverse is also y equal 1 over x. එහෙමයි ඉන්නේ දෙන්නයි. එකක් y equal x line එක අනිත් එක මෙන්න මෙයා. දෙන්නයි නෙමෙයි අතන තව කීප දෙනෙක් ඉන්නවා. මෙන්න මේ දෙන්නත් එහෙම වෙන්න ඕනේ. මේ දෙන්නත් එහෙම වෙන්න. එහෙමයි තව ඉන්න පුළුවන්. හැබැයි මේ දෙන්න තමයි ප්‍රසිද්ධ. Right. So now we have done the relations part. Now we are moving to the functions. Second part of your syllabus topic. So this is very easy because functions are special case of relations. So that means every function is a relation, but not every relation is a function. Okay. So how do you define a function? So this is the formal definition, but I will give you the informal sort of a definition first. So if a relation satisfy following two properties, we can say that that relation is a function. What are those two properties? Number one, uniqueness property. So that means input from one value must map to exactly one value. So this is okay. But if there's a situation like this, value from domain side is mapped to not one, more than one. This is not a function. Right? So this is fine. Even this is fine. Because value in x is mapped to value in one value in y. Value in x is mapped to one value in y. So you just concentrate on that definition. If a value in domain is mapped to one value in y, right? One value in y, one value in y, one value in y, it's a function. But if there's a situation where one value in x is mapped to more than one value, that is not a function. That is relation, but not a function. So basically, one-to-one are functions. Many-to-one are also functions. But definitely one-to-many are not functions. Many-to-many are also not functions. So one-to-one and many-to-one are functions. One-to-many and many-to-many are not functions. So that is the uniqueness property. So the second property is no unmapped values in the domain side. So in the domain side, all the values must be mapped. If you have at least one unmapped value, we call it orphan value, anate. So then it is not a function. Still it is a relation, but not a function. Of course, you can have unmapped values in the range side. Still it is a function. But the moment you have unmapped value in the domain side, it is not a function. This is how you define function. So therefore, it must satisfy the uniqueness property and no unmapped value in the domain side property. So then it is a function. Okay. So this is the formal definition. A function is a special type of relation that assigns each element in a set A or domain to the exactly one element in set B. Right? Each element. So each element means there can't be any orphan values. Okay. So these are some examples. So one-to-one relations are obviously functions because one value is mapped to one. And of course, there must not be any orphan values. So this is a many-to-one. Don't worry, many-to-one are functions because one value is mapped to one value. 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 If one value is mapped to more than one value, then it is not a function. So that is why one-to-many are not functions. Many-to-one are functions. One-to-many are not functions. One value is mapped to more than one. Many-to-many are not functions because many-to-many also has a one-to-many nature. And of course, if you have orphan values in the domain side, that is not a function. When a function maybe it's one-to-many, maybe it's many-to-many, or maybe it has orphan values. Or while these are happening, the orphan values are also there. It's both one-to-many and orphan values. Or just orphan values, or just one-to-many. Or it's many-to-many and orphan values, or just many-to-many. So those are not functions. So if you want to check a particular graph, say you are given a graph, not anything else. How do you check whether it's a function? It's very easy. So we call it vertical line test. Just take a vertical line, right? Vertical line parallel to y-axis. And take this line from minus infinity to plus infinity. If at least at one point, if that cross the graph more than more than one times, it is not a function. So that means it is for one x there are multiple y. If there is at least one such situation, that means it violate or it's basically one to many. Of course, the other thing is you need to check whether there are orphan values in the domain which are not mapped. Okay. But vertical line test is very useful to check whether it's a function or not. So what you have learned in your O level are pretty much functions like straight lines, functions, parabolic shapes, functions, because you can see those are many to one. Many x can have one y, but that is okay. Many to one are functions. But these are not functions. You can see one x value, many y value. These are not functions. One x value, many y value. Right? For example, this is a function because it passed vertical value test. Okay? But this is not a function because you can see for one x value, there are multiple possible y values. Right? Even this is a function. Sine wave function because vertical test pass. But if you take something like this, that is not a function because for one x value, there are multiple y values. Okay. Is it clear? Right. So this is the notation we use in function. Actually, we use this notation for relations also most of the time. But this notation is more specifically used for functions. That is why we often use the word letter F also. Fx. So relation notation is R. Say R x map to y. How? Y equal to x squared plus 3. But this is the function notation. So we can say fx equal x squared. Fx equal 2x plus 3. Or you can simply say y equal to x plus 3 also. And this is the function notation. This is the relation notation. Okay. This is called f of x. F of x is x squared. Like casually we say fx, f5, f1, or more formally f of 2, f of 0. Sometimes when they show function as a sort of a machine, because you can have multiple input, but one output function. ගොඩක් අය ඉමේජ් වලින් වාට සමහරට පෙන්නන්නේ ඒකල මැෂින් එකක් කියලා ෆන්ක්ෂන් එකක් කියලා. Something like this. Input you call it function machine. සමහරට කියන function machine එකක් කියලා. Because it's you can visualize it like that, right? So there must be for one input there must be only one output. Function machine එක මේ x දානකොට මෙහෙනිත් ඇවිල්ලා එකක් මෙහෙන් වෙන එකක් එන්න බෑ. Okay, then it is not a function. It's a relation but not a function. In function, your x1 can end up with y1, x2 can also end up with y1, but x1 cannot end up with both y1 and y2. Then it is not a function. Right, so now we'll look at few more concepts related to functions. So we'll look at what is mean by injective function, surjective function, and bijective function. Don't worry, these are just words. You නිකන් වචන විතරයි යා. වචන වලට බය නම් එහෙම ඔයගොල්ලෝ IT කරන්නත් එපා වෙන මොකුත් කරන්නත් එපා. සමහර මිනිස්සු හරි නේද? සමහර මිනිස්සු ලංකාවෙන් මෝඩයන් අන්දන්නේ නැත්තේ නේද? බර වචන ටිකක් දානවා. විශේෂයෙන්ම මහාචාර්යවරු කියලා ඉන්න සෙට් එකක් ඉන්නවනේ. මම කියන්නේ හැම මහාචාර්යවරු නෙමෙයි. තමන් පඬිතයි කියලා පෙන්නන මහාචාර්යවරු ඉන්නවනේ. ඒගොල්ලෝ හැමතිස්සෙම ලොකු වචන දාලා කතා කරනවා. මේක වියුක්තව ගන්න ඕන. මේ સંદર્ભය ඇතුළේ ඉඳලා අපි මේක බලන්න ඕන. නයිසાર્ගික කියයි, හෙජමනීය කියයි. ඉන්නේ දේශපාලන මහාචාර්යවරු. ඒගොල්ලෝ හිතනවා එතකොට සමෝඩ මිනිස්සු හිතනවා අපට උඩු මාරු උගතනේ. ඒගොල්ලන්ට අනිත් අය නොතේරෙන භාෂාවෙන් කතා කරනවා. වචන සෙත් පොඩ්ඩ වචන ටිකක් ඉගෙනගෙන. ඒ වගේ තව සෙට් එකක් ඉන්නවනේ දර එක්ස් කණ්ඩායම කියලා ඉන්නවා. අපිට සාමාන්‍ය මිනිස්සුන් නොතේරෙන වචන සෙට් එකක් එළියට දාන එක. කාලෙන් කාලෙ. මේ දවස්වල එළියට දාලා තියෙන වචනේ මොකක්ද? කාටද කියන්නේ මොකද්ද? එක්ස් කණ්ඩායම මේ දවස්වල එළියට දාලා තියෙන වචනේ. විතර කියන වචනේ. ඒගොල්ලෝ එහෙම දැන් කාලෙන් කාලට මොකක් හරි වචනයක් කියනවා. You don't know. You are not interested in those things, right? Right. So therefore, these are just ඕන දැන් කියන්න පුළුවන් පායි. ගිහිල්ලා නේද? Injective function, surjective function, bijective function කියලා. එහෙම ආතල් ගන්න කැමති නැහැ. So these are just words, okay? Right. What is mean by injective function? Injective is another name for one-to-one function. So either you can call it one-to-one function or you can call it injective function. පොඩි ආතල්යක් ගන්න ඕන කියන්නේ injective function එකක් කියලා. Right? So it's just another name for one-to-one function. If a function is injective, it means it's a one-to-one function. It's not a one-to-many or many-to-one or many-to-many. Right? Something like y equal x. It's a one-to-one function. Is that only one-to-one function? No. Y equal y equal 1 over x is also one-to-one function, right? Yes, y equal 1 over x. Even exponential function, y equal 10 to the power x. Those are one-to-one functions. Okay. Right. So injective function is another name for one-to-one function. So that means for x1, if there's y1, if you have x2, if fx1 and fx2 is there, if it is 1-to-1, x1 must be x2. If fx1 equal fx2, x1 must be x2. Can you understand that definition? සමහර example එකේ ඔය වගේ තමයි කියන්නේ. So what is මේකෙන් කියන්නේ මොකක්ද කියලාද? 1-to-1 කියලා. බලන්න මේක කියන එක තේරෙනවද කියලා? මේ කියන්නේ 1-to-1 කියලා technical විදියට. Abstract විදියට. Say we have function f. So when you have x1, it goes to a particular value. And this says when you have x2 also, it goes to the same value. That is why fx1 is fx2. If that is the case, and if you know that this is injective function, that means if you know that this is one-to-one function, if this is the case, x1 must be same as x2. මෙහෙම වුණා නම් මේක 1-to-1 function එකක් නම් අනිවාර්යෙන්ම ආව කියන x1 සහ x2 එකම වෙන්න ඕන. ඒ කියන්නේ මේ දෙන්න එකක් වෙන්න ඕන. එහෙම නැත්නම් මේක many-to-one වෙනවා. ඔයානේ කියන්නේ 1-to-1 කියලා. ඔයා කියලා 1-to-1 කියලා ඔයා මෙහෙම කියනවා නම් අපිට කියන්න පුළුවන් එහෙනම් අනිවාර්යෙන්ම වගේ x1 සමාන සහ x2 සමානයි කියලා. එහෙම නොවෙනවා නම් මේක injective නෙමෙයි. හරි. So that is a way of formally defining something. Formal definitions, okay? Because maths is a formal science subject, sometimes we need formal definitions. Not sometimes, all the time. Right, so that is called injective. So next one is surjective or onto function. මතකද දැන් අර ඔයගොල්ලෝ සර්ච් කරපු වෙලාවෙත් මම දැන් කොහේ හරි onto කියලා දිනුනා. ඔයගොල්ලෝ මෙන්න මේ හරි මම දැන් onto කියලා. මේකේ onto function. වෙනවද onto function? පේනවද surjection මම දැන් search කරේ function කියලා හරි ඉතින් surjection not a surjection මේ පේනවද on to so this is the inverse of a function දැන් අපි මේ කතා කරන් යන්නේ ඔය ටික තමයි domain range නේද අපි ඔක්කොම කතා කරලා තියෙන්නේ this is a vertical test vertical line test පේනවද මෙයා fail වෙන vertical line test not a function okay not a function so if you have any doubt you need to ask okay right so what is mean by surjective function or onto function another name for surjective function is onto function so if there's a function having no unmapped values in the range side it is a surjective function so surjective function is a function where there are no unmapped values in the range side. So in other words, it's something like saying your range is same as codomain. In general, range is a subset of codomain. Range is a subset of codomain. So that means your range may, your codomain may have unmapped values. But if your range is same as codomain, that means there is no unmapped value like this. Something like this. All the values have a mapping. So then we call it surjective or onto. So this is called into function. Surjective නැතිවට අපි කියන්නේ into කියලා. මේ පැත්තේ open අනාතයෝ ඉන්නවා. අනාතයෝ නැත්නම් surjective. But you only look at the range side. Okay. Sometimes we draw it like this. So this is onto function. And this is මෙයාගේ මේ අනාතය එළිය ඉන්නවා because this is your codomain and this is your range is inside codomain here range is same as codomain so this is called onto function or surjective and this is called into function not surjective because there are values in your codomain which are not in your range now තේරෙනවද අර codomain කියලා එකක් ආයි define කරේ ඇයි කියලා okay Now, is it clear what is injective? That is simply one-to-one. Surjective, that means it's an onto function, not into function. That means there are no unmapped values in the range side. In other words, your range is same as codomain. So the third word that we use is bijective function. Bijective. So bijective means it's both injective and surjective. If there's a function which is both injective and surjective, that is both one-to-one and no open values in the range side, we call it a bijective function. So this is definitely a bijective function because it's one-to-one and there are no open values in the range side. It's a bijective function. So these are some examples. So remember, a function is one-to-one, no many-to-one, and no open values in the domain side. Then පටලවා ගන්න එපා හරි. We have already defined what is function is. Function means what? It must be either one-to-one, no many-to-one, and no open values in the domain side. So then it's a function. So then if there's no open values in the range side, it is surjective. If it is one-to-one, it is injective. If it is both injective and surjective, it is bijective. පටලවා ගන්න එපා හරි. Function එකක් කියන්නේ මොකද්ද? not a function කියන්නේ මොකද්ද? Injective කියන්නේ මොකද්ද? Surjective කියන්නේ මොකද්ද? Bijective කියන්නේ. Bijective වෙනවා injective surjective දෙකම වෙනවා. Right, so this one is not a function. Why? Because you have one-to-many. Right? If you have one-to-many, it is not a function. And this is a general function. You can see it's many to 1. That is fine. It's many to 1. And no open values in the domain side. So if it is many to 1 and no open values in the domain side, it is a function. Now you need to check whether is it injective or surjective. Obviously, it is not injective because it is not 1 to 1, it is many to 1. And also there are open values in the range side. So therefore it is not surjective also. So therefore it is not bijective. It's another general function. What about this? So this is function. All the values are mapped, no open values here, and it is 1 to 1. So therefore, definitely we can say it's a function. Right? It's a function. And also it's an injective function because it's 1 to 1. 1 to 1. But it is not surjective because there are open values in the range side. So therefore it is injective but not surjective. So therefore it's simply an injective function. Okay, injective function. Okay, just give me 1 minute. Okay, right. So what about the next one, fourth one? It's definitely a function, right? No open values in the domain side. And also it is 1 to 1. So not 1 to 1, many to 1. That is fine. Many to 1 are functions. Therefore it's a function. Now is it 1 to 1? No. Therefore it is not injective. So therefore it is not bijective also. But there are no open values in the range side. So therefore it is surjective. So therefore it's a surjective function. So then what about this? This is definitely a function because it's 1 to 1 and no open value. So therefore it's a function. And also it is 1 to 1. So therefore it is injective. And also there are no open values in the range side. So therefore it is surjective. If it is injective and surjective, it is a bijective function. And you can say it's a function, you can say it's an injective function, you can say it's a surjective function, and you can even say it's a bijective function. Okay. But if it is not a function, don't check whether it's injective, bijective, surjective, because it doesn't matter if it is not a function. Is it clear?
Yes, sir.
Right. So now we move on to the inverse of a function. Actually, there's nothing new to learn because inverse of function is same as inverse of a relation. Only thing is if your relation is a function, now we call it's inverse of a function. For example, if you take y equal 2x plus 3, it's a function. So what is the inverse of this function? Then 2x equal y minus 3, x equal half of y minus 3. That is y equal half of x minus 3. So this is your function. This relation is a function. And this is the inverse of that function, which is a mirror image on y equal x line. Okay. So let's draw it again. Y equal 2x plus 3. Y equal 2x plus 3. What is the inverse? Half of x minus 3. Okay. And if you draw y equal x line, you can see the. Okay, so this is y equal 2x plus 3, right? 2x plus 2. So you can clearly see that it is inverse. And you can see that this is your function and this is the inverse of that. And you can see this is really a function, right? Because it's 1 to 1. And this is also a function because it is also 1 to 1. So there are situations you have a function and its inverse is also a function. But that is not always the case. So there can be a situation where you have a function, its inverse is not a function. Its inverse exists. Of course, every relation there's inverse. Every function also there's inverse. But there is a situation where you have a function and its inverse is also function. Second scenario is you have a function, its inverse is not a function, it's just a normal relation. But for any relation, there's an inverse. Okay? මම කියනවා හරියට තේරුම් ගන්න. හරි. Right. So in what kind of situation inverse of a function is also a function? Right. Inverse of a function must also be a function. So if your original function is bijective function, right? If your original function is a bijective function, its inverse is also a function. I'm not saying that its inverse is a bijective function. What I'm telling is, if your function is a bijective function, its inverse is also a function. If not, it have an inverse. It has an inverse, but its inverse is not a function. It's normal relation. Okay. If a function is not bijective, still it may have inverse. Not it may have, it has an inverse. Okay, let me change it because may කිව්වම ඉස්සමට ඉතින් සමානලට තියෙනවා කියලා. It has an inverse, but the inverse will be a non-function relation. Right, now it's better. Right, so that means not all the functions have their inverse as functions. Only some functions have their inverse also function. So what are those some functions? Those are the bijective functions. Okay. Now can you, if you think about it, you can see the reason. Why is it only bijective functions are having inverse functions? Others are having inverse but not those are not in functions. If you can explain that, so that means you are really logical thinker. So what is the statement? If a function is bijective, its inverse is a function. Else, its inverse is not a function. So the reason, my question is why? Or I can ask like this: why is it non-bijective functions are not inverse of non-bijective functions are not a function? Why is it? Why is it? So number one reason is a function will be not a bijective function because it is not injective or because it is not surjective. So let's take the easier one. Maybe it is not bijective because it is not surjective. That means it has open values in the range side. Even if you have open values in the range side, we say it's not surjective. And when you have open values in the range side, when you take the inverse, you have open values in the domain side. Because your range becomes domain. So then when you have open values in the domain side, it violates the definition of function. Because if it is a function, you can't have open values in the domain side. So therefore, automatically it becomes not a function. Of course, the inverse exists, but inverse is not a function because now you have open values in the domain side. So that is why we say bijective need to be surjective. So then if it is one-to-one only, your inverse is also 1 to 1. So what is the other possibility for function? Many to 1. Because many to 1 are also functions. But if it is a many to 1, the inverse become 1 to many. 1 to many are not functions. Because many to 1 is your original function, is many to 1 means your inverse is 1 to many. And obviously 1 to many are not functions. So now you should see that this concept of injective, surjective, bijective is made, right, simply to define which functions have inverse as a function, which functions do not have inverse as a function. So basically we guard our function so that its inverse is also a function. How to guard it? Check whether it's 1 to 1, check whether there are open values in the range. So that means your inverse is also 1 to 1, and inverse don't have open values in the domain.
So can you explain again?
Can you explain what?
Can you explain the last few explanations?
What do you mean by last few explanation? You want me to explain what is?
What is that?
Because when you say last few, I don't know from which point onwards I need to explain. If you tell me I can't understand this part, I can explain.
How does the bijective function? How does not a bijective function is not a function? How does the
The
bijective
bijective function is a function.
not a bijective function? How does the inverse of the not a bijective function is not a function?
Yes. Say this is not a bijective function. This is a function. Okay, this is a function. This is say A is mapped to A1 is mapped to B1. A2 is mapped to B2. Right? A3 is mapped to B3. And also A4 is mapped to B3. And this is definitely a function because this doesn't violate the definition of function. What is the definition of function? There must not be any open values in the domain side, no open values in the domain side. And for one particular value in domain, it must have unique y value. Yes, unique y value, unique y value, unique y value, unique y value. So therefore, this is a function. But if you take the inverse of this is the inverse. B1, B2, B3, A1, A2, A3, A4. So now B1 is mapped to A1. B2 is mapped to A2. And B3 is mapped to both A2 and A3. So if one value is mapped to multiple values, this is not a function. Of course, this is the inverse. If this is F inverse. But clearly, this is not a function. So you can see when this violate bijective nature, your inverse is not a function. This is not bijective, and of course, this is not a function.
Okay, sir.
Okay, so likewise. The other thing is check whether if you have open values here, that means it is not a surjective. So that means in the inverse, you have an open value here. So that means again, it violates the definition of function. Because if you have open values in the domain side, it is not a function. Right. So if you think very clearly, this is super simple concept. This is not rocket science. Only thing is you need to separate out all these concepts. Don't mix things together. Right. What is a relation? What is a function? What is the inverse? What is mean by inverse of a relation? What is mean by inverse of a function? So inverse of function can be a function, or inverse of function may be not a function. If an inverse of function is a function, this original function must be bijective. So that is how you make it, right? Argument. Right? So this is the explanation, right? So injective guarantee that inverse is also 1 to 1. Surjective guarantee that inverse has no unmapped values, so open values in the domain side. So that basically guard against guard so that your inverse is a function. Okay. Right. So this is definitely a function, right? This is a function because it's satisfied the vertical line test also. But definitely this is a function, but its inverse is not going to be a function because it's many to one. Many x has one y value. That means its inverse is going to be, if this is many to one, inverse is one to many. Inverse is one to many. Okay. So therefore, this is a function, but it's not a bijective function. This one's inverse is a relation, not a function. But this is definitely a bijective function. You can see it's one to one. And assume not open values. And its inverse is going to be another function. Okay, another function. ChatGPT පොඩ අමාරුයි දාන්න බලන්න. ChatGPT අඳී දාන්න ටිකක් ChatGPT ට දාඩිය දාන්න ගනි. Draw the inverse. Draw this function with its inverse in same graph. තව graph එක දුන්නේ නැහැ. අපේ යාගෙන function එක දෙන්නලු. මම අපිට උනම් graph එක දෙන්න. Right. So let's see whether it can do it. Thanks for the image. අපේ විනය අඳින්නේ නැහැ වගේ නේද? අපටිය. නෑ අඳිනවා. හැබැයි මේ හරි එකක් ඇඳේ නෑනේ බොරු ඇඳන්න පෙන්නනවනේ. මෙහෙමයි කියලා. It's not. I think the ChatGPT is not good at doing that yet. එයාට මේක ඇඳගන්න බෑ තාම. හරි. එයා ඒකද මේ sample එකක් ඇඳලා පෙන්නනවා. mirror image එක කියලා පේනවා. sample එකක් ඇඳලා පෙන්නනවා. එයාට මේක ඇඳගන්න තරම් තාම බෑලු. Okay. Specific function. එයා කියනවා function එක දුන්නොත් කරන්නලු. Okay. function එක දුන්නොත් කරන්නලු මෙහෙම දෙනවන්න නම් මට අඳින්න බෑලු. හරි. මම කියයි බොහෝට කරගන්න බැරි වෙයි කියලා යාට. Right. So that is what bijective functions are. So bijective functions have its inverse also as a function. Otherwise, its inverse is not a function. Okay. Right. So how to find the inverse is the same, whether it's function or relation, right? Right. So do this as exercise. Take a piece of paper. Draw the inverse of this function in a graph. ඉස්සෙල්ලා y සමාන x line එක ඇඳගෙන sketch කරන්න නිකන් rough අඳින්න. rough අඳින්න. මෙයාගේ mirror image එක අඳින්න වට තියෙනවා. පුළුවන් දැනකින් පටන් ගන්න. මෙන්න මේ වගේ දැනකින් පටන් ගන්න ලේසි. ඔන්න ඔහොම ගිහිල්ලා ඉතින් බා. ඔයගොල්ලන්ට අපිට වැඩි චිත්‍ර අඳින්න පුළුවන්. මේක ඇලෝ මේයි. ඔන්න ඔහොම තමයි එන්නේ. Something like this. Okay. So it looks like it is not a function. Right? It is not a function. Of course, this is a function, but its inverse is not a function. Definitely, its inverse is not a function. Okay. So why do we say that its inverse is not a function? So this blue line is the inverse. But when we line එක ගමන් කැපෙනවා. දැන් දෙකකින්. ලාවට වගේ කැපිලා යනවා. මෙන්න මේ වගේ. මේ වගේ තැන්වල සමහර කැපෙනවා. But red one is definitely a function. You can see, but its inverse is not a function. Because this red one, you can see there's a minute one. Make a minute one thing again, 1 to many. Okay. So 1 to many is not a function. But definitely red one is a function, but its inverse is not a function. Right. So again, inverse of an inverse is the same thing. Right? You know that, right? Because inverse of a relation is the same thing. Then if inverse of F inverse is F. Right? F inverse ki inverse ගත්තමට I F එනවා. If your function is S, its inverse is also X, because that is a special case. Because when you draw the mirror image on Y equal X line, the Y equal X line is itself. So therefore, that is a special case where if your function is fx, its inverse is also fx. හරිනේ y equal x කියලා ගත්තම I xy මාරු කරලා ලිව්වා. I මාරු කරලා ලිව්වා. ඉතින් I එන්නේ y සමාන x සමාන. So that is a special case. Right? That is a special function where its inverse is itself. Okay. Right. So now we move on to composition of a function. Composite function. Okay. Sometimes we call it function of a function. So this is how you visualize it. This is your function machine. And now you give this output to another function. Right? So this output, this is F1 and this is F2. So first we do F1, then we do F2. Okay. So that is called composite function. මෙයාගේ output එක I මේ විදිහට process කරනවා. So this is an example. So this is how you write it in symbolic way. Say this is my fx, this is my gx. What we do first? We do fx first. Then to the result of fx, we do g. So this is g of fx. And g of fx. Or else we can write it like g0 f. මේ g0 කියලා කියන්නේ. මේක නිකන් බිඳුව කියන අදහස නෙමෙයි තියෙන්නේ. මේ notation එක. g0 f. So either you can write this as g0 f or g of fx. Another way of writing g of fx is g0 f. Again, it's a notation. So mathematicians can give notations, right? And remember, g0f is not same as f0g. Because f0g is f of gx. f0g. So this is not. ඒක හරියට මේක කාලා අත හොදනවා. කාලා අත හේතුව මොකද වෙන්නේ? කෑවේ කුණුත් එක්ක. හැබැයි දැන් කාලි වල අත ක්ලීන්. මේක අත හොදලා කනවා. කෑවේ ක්ලීන් පිට. අත හොදලා තමයි කෑවේ. හැබැයි දැන් අතේ කුණු. අතේ ඉඳුල්. කාලා අත හොදනවා, අත හොදලා කනවා. Two different outcomes. So therefore, g of fx is not same as f of gx. Right? It is not the same. It is not the same. Okay. So those are very important things. And සමහරු ඉගෙනගෙන ඉවරලා ජොබ් එකක් ගැන කල්පනා කරනවා. ඉගෙනගෙන ඉස්සෙල්ලා ඉගෙන ගන්නවා. ඊට පස්සේ එළියට ඇවිල්ලා කල්පනා කරලා දැන් මම මොකද්ද කරන්නේ ජොබ් එක කියලා. තව කොටසක් ඉන්නවා. ඉස්සෙල්ලා කල්පනා කරන මම මොකද්ද කරන්නේ? මෙහෙම ගෙදරටලා ඉන්න බෑ කාලා ගන්න එක වගේ. රටට බරක් වෙන්නත් බෑ. ඒකට හරියන දේ ඉගෙන ගන්න. හරි. ඉගෙන ගන්න ඕන දේ කල්පනා කරලා ඒකට හරියන දේ ඉගෙන ගන්න. තව කට්ටිය ඉගෙනගෙන ඉවරලා කල්පනා කරනවා දැන් මම මොකද්ද මේ ඉගෙනගත්ත දේට අනුව කරන්න කියලා. So f of g, g of f. Okay. Two different things. So this is g0f. First we do f. To that result we do g. So first we do f. සමහරට පටලව ගන්නවා ඔයගොල්ලෝ හරි. මේ ඉස්සෙල්ලා කරන එක නේද මෙතනදී. ඇතුලේ ඉන්නේ. මොකද ඉස්සෙල්ලා කරන එක නේද? That is this. And then we do this. To that result we do g. So therefore don't get confused. So therefore when we say g0f, it is g of fx, but when you draw, first we have f and then you have g. If you are not very serious, you miss it. You miss it. ඒ සීරියස් නැති අය. ඒගොල්ලෝ ෆේල් වෙන්න ඕන. ඒගොල්ලෝ ෆේල් වෙන්න ඕන. ඒක සීරියස් නැති අය වරයි යන්නේ බෑ මේ කමන. Right, so g0f means g of fx. f0g means f of gx. And those are two different things. Those are two different things. Okay. So this is your g. This is your gx. And this is your fx. So fx is mapping subpart of your gx into this. Okay. So this is the domain of g. This is the domain of g. Okay. And this is the range of g. Range of g. And this is the domain of f. And this is the range of f. And if when you do f0g, that means first you do g and to that result you do f. So therefore, though these are in the domain, when you do f0g, these are only possibilities because it must coming from here. Of course, these are also there, but these are not the domain of f. So therefore, from here, we take only these things and map it again. So that is your final result. So these things you can't map because these are not in the domain of f. These things are not mapped because these are not the result from this g. So therefore, actually what happens is from here, you map it to here. From there, you take only this thing and map it to here. So therefore, the final result of f0g is only this part. This part. Okay. So this is your final result. So this is not there because we don't care about this because these are not input from this. Think about it. එකපාර තේරෙන්න ගන්න හොඳට කල්පනා කරලා තේරෙයි. හරි ඉතින් first interview එකෙන් second interview එකට යනවා. second interview එකෙන් third නේද? third එකට යනවා. ඒතර මෙතන ඉන්න පුළුවන් මේක කරන්න පුළුවන් කට්ටිය. නමුත් කරන්න පුළුවන් කට්ටිය මෙතනින් පිළිතුන්නේ නැහැ. ඒතර ඒගොල්ලෝ first interview ආවනම් මෙහෙන් ආවිල්ලා මේකට අහුවෙන්න තියෙනවා. නමුත් මේගොල්ලෝ ගන්න නැහැ අපි interview එක. මොකද මේගොල්ලෝ first interview හිටියේ නැහැ. සමහරවිට මේගොල්ලෝ second interview කරගන්න පුළුවන් කට්ටිය ඉතින් මොනවා කරන්නද? නැත්නම් මේගොල්ලෝ ඉස්සෙල්ලා IQ test එකක් දෙනවා ඊට පස්සේ interview එක තියෙනවා. මේ ඉන්නේ IQ test එකට ඇවිල්ලා pass වෙච්ච කට්ටිය. IQ test එකට ඇවිල්ලා pass වෙච්ච කට්ටිය තමයි මෙතන ඉන්නේ දැන්. right මේ ඉන්නේ. හැබැයි ඒගොල්ලන්ගෙන් interview pass වෙන්නේ මේගොල්ලෝ. interview එකට ගන්න මේගොල්ලෝ. ඒතර interview එකෙන් pass වෙන්නත් ඕන ඕගොල්ලෝ. ඔන්න ඉන්නවා. මේගොල්ලන්ව interview එකට ගන්න විදියක් නැහැ. ගත්තට වැඩක් නැහැ. ඒගොල්ලෝ IQ pass කරනවා. into pass වුණාට. ඒක අපි ගන්න අන්තිමට IQ pass වෙලා into pass වෙච්ච කට්ටිය විතරයි. මේගොල්ලෝ IQ pass වුණාට interview select ගියේ නැහැ. නැත්නම් interview ගියේ නැහැ. හරි මොනාරි අවුලක් වුණා. මේගොල්ලෝ interview pass වුණාට IQ එක fail වෙනවා. අපි ඉතින් මේක පිළිවෙලට ගන්නත් ඕනේ මේක කළා තමයි මේක කරන්න ඕන. හරි. මේ කරන්න පුළුවන් කට්ටිය නමුත් ඒගොල්ලන් කරන්න පුළුවන් කට්ටිය වුණාට ඉන්ටර්විව් එකේ ඒගොල්ලෝ ක්වොලිෆයි වුන්නේ නැහැ ඉන්ටර්විව් එකට. මොකද මෙහෙන් ආවේ නැති යනවා. So likewise try to build a story. Okay. Right. So finding these composite functions are super easy. Super easy. Say this is my fx. This is my gx. I want to find g0 of x. So that means g of fx. So now you write gx, that is this, but instead of x, you need to write fx. So you write gx. Gx is what? X squared. X squared. Right? If it is gx, x squared, but it's not gx, it's g of fx. So therefore, rather than x, you need to write fx. Fx is 2x plus 3. So this is your final answer. So g0 fx is 2x plus 3 square.
Sir, I didn't understand.
So you want to find g0 fx. So g0 fx by definition is g of fx. Okay. So what is g of x? Forget about the g of fx. What is g of x? G of x is x squared. G of x is x squared. X squared. But what we did is not g of x, g of fx. So therefore, what is fx? 2x plus 3. So therefore, rather than x squared, you need to write fx, which is 2x plus 3. So therefore, g0 fx, so g of fx is 2x plus 3 square. Right? Square. And similarly, if you want f0 g, that is f of gx. So what is fx? Because we are interested in this fx, 2x plus 3. 2x plus 3. But what I need is not fx, f of gx. So then what is gx? Gx is x squared. So that means 2 of x squared plus 3. So therefore f0 gx is 2x squared plus 3. And clearly those are two different things. So we found g0 f and f0 g. Okay. Or you can write it like this, g of fx. Fx is 2x plus 3. And what is gx? X squared. So then this is your x, it's squared. Okay, so I think there's a typing mistake. So this must be 2x. Let me fix that also. So there's a typing mistake. Right, 2x plus 3, it's squared. Okay, so now it is correct. I will upload it again. Second one, f of gx means gx is x squared. That is f of x squared. So f of x is now not f. What we need is not f of x, rather f of x squared. So therefore, whenever you have x, you must have x squared. 2x squared plus 3. And we can have composite functions on its own. That is something like f of fx, g of gx. Those are possible. Right? Say this is my function 2x plus 3. Then what about f of fx? That is f of fx is 2x plus 3. So f of x is this. That means rather than x, you need to find 2x plus 3. 2 times 2x plus 3 plus 3. That is 4x plus 3 into 2 is 6. 6 plus 3 is 9. So the final answer is 4x plus 9. And also you can find f1, f2, f3 also, right? For example, if fx is 2x plus 3, what is f0? 2 times 0 plus 3, that is 3. What is f5? 2 times 5 plus 3, that is 30. So same thing, right? Similar concept. I do this. Fx is x squared. Gx is x minus 1. Find f0 g5. Tagalahan. So you can do it in two different ways. One way is f0 g5 is f of g5, right? F of g5. And what is g5? What is g5? That means rather than x, you have 5 here, 5 minus 1, which is 4. Now you know the g5. So therefore it is f of 4. And what is f of 4? F of x is x squared. Then f of 4 is 4 squared, which is 60. That is the answer. What is the other way? This is one way. Other way is you write f of g5. Forget about the f of g5. You write f of gx. f0 gx is f of gx. That is, you write fx, but instead of x, you write gx. You write fx, but instead of x, you write gx, which is x minus 1. That is x minus 1 squared. So that is f0 gx. So now I need f0 g5. f0 g5. So that means here you substitute 5. 5 minus 1 squared. 5 minus 1 is 4. 4 squared is 16. Yes, you get the same answer. You get the same answer. So how do you visualize this? The concept of composite function. Okay. So let's go search. අපි මෙයාට පොඩි වැඩක් දීලා යනවා. නිකන් තියන්න හොඳ නැහැ chat GPT එක. Visualize composite function using function as a machine. Okay. බලන්න මෙයා පටන් ගන්නද කියලා. බබා පාට දාන්න බෑ දැන් ඇඳලා දෙන්න ඕන. මිනිහා අඳින්නේ නැහැ අඳිනවනේ. මිනිහා හරි ආසයි ඒවට මේ කියන අවුස්සම්. Great way to understand how functions work together. Right? බලමු මෙයා අඳීද කියලා පොරටෝක් දුන්නාට එයා පොරටෝක් දුන්නාට සමහරට අඳින්නේ නැහැ හරි. ඉගෙන ගන්න එකානේ පොඩි එකන් තමයි. Right, so let's see. Function or composite function. ඔයන් තේරෙන්නේ නැද්ද මේ මාත් එක්ක ඉගෙන ගන්නකොට ලේසි කියලා chat GPT එක ඉගෙන ගන්න එක? හරි. ඔයගොල්ලන්ට තේරි තව චුට්ට දවසක් යනකොට මේ chat GPT එක්ක මට ඉගෙන ගන්න පුළුවන් කියලා හරි. ඔයගොල්ලන් නෙමෙයි හැමෝටම තේරි තව චුට්ට දවසක් යනකොට. අපි දැන් වෙන ජොබ් එකක් හොයාගන්න ඔයා try කරන්න. තව ටික දවසක් ගියාම ටීචර්ස්ලා ඕන වෙන්නේ නැහැ ලෙක්චරර්ස්ලා. Right. So it should be something like this. Right. So let me draw it. Right. So it should be something like this. So this is my function, first function. Okay. And this is my second function. Okay. And composite function is something like you have a big machine. There you have the output and this. So therefore you do it, give it to this and take and this, put it to this. Rather than that, you do give it to this big function. For example, if this is fx is x squared, if this is gx is x plus 1, so then this is something like x squared plus 1. Okay, x squared plus 1. Okay. If it is other way, g of fx, it is like x plus 1 squared. Okay. මේ ඇඳලා නෑ මං හිතන්නේ අනාගතද තනින්නේ. ඔව් එච්චර හොඳට ඇඳලා නෑ. එයාගේ ඇතුලේ තියෙන g සහ ඔව් අඳින්න ගියාට මොකද වැඩේ එච්චර හොඳට ඇඳලා නෑ. හොඳේ. මල් පෝච්චියක් වගේ ඇඳලා තියෙනවා මොකද්ද මන් දන්නේ. හරි. වැඩේ චාටලා. Didn't fully follow instructions. Okay. Right. So now we move on to our next subtopic, combination of functions. බලන්න කොච්චර තියෙනවද කරා. තව ටිකක් තියෙනවානේ. Right. So we'll do that. Yeah, we'll do that in the next class. Okay. මොකද ඉවර කරන්න වෙලා මදි. Right. So we'll do that in the next class. අද ටිකක් මම වෙලා ගත්තා මොකද relational algebra වල ටිකක් මට වෙලා ඕන වුණා. හරි. ඊට පස්සේ දැන් අයියෙන් කරනවා. දැන් අයියෙන් පටන් ගන්න topic නෑ. දැන් තියෙන දඩබඩ ගාලා කරලා ඉවර කරන topic, right? So anyway we have not finished this. Right. We have not finished this, okay? Right. So we stop at this point so that